The human brain contains roughly 86 billion neurons. Each neuron connects to thousands of others, creating a network so vast that mapping even 1% of it remains beyond our current capabilities. Somewhere within this biological maze, you store everything you are: your first memory of rain, the face of someone you loved, the taste of bread your grandmother baked. These are not files on a hard drive. They are patterns of electrical activity, cascades of chemicals, structural changes in proteins too small to see. Memory is the most intimate technology humanity possesses, and we barely understand how it works. For thousands of years, cultures across the globe imagined shortcuts to knowledge. Ancient warriors believed consuming the heart of a brave enemy would transfer courage directly into their spirit. Medieval scholars thought swallowing ground pearls could enhance wisdom. Pacific Island cultures practiced ritual consumption of the deceased, hoping to absorb their memories and skills. These were not mere superstitions. They represented a fundamental human desire to acquire knowledge without the pain of learning, to become someone else without the years of transformation. Modern neuroscience has revealed something extraordinary. Memory does not reside in a single location. When you recall your childhood home, neurons fire across your visual cortex, your emotional centers, your motor regions that remember how you moved through those rooms. A memory is not stored like a photograph in an album. It is reconstructed each time you remember it, assembled from fragments scattered throughout your brain, like pieces of a puzzle that changes shape every time you put it together. This reconstruction process explains why memory feels so reliable, yet proves so unreliable. You remember your 10th birthday party with perfect clarity: the blue frosting on the cake, your friend's laughter, the weight of the gift in your hands. Neuroscientists can demonstrate that half of those details are probably wrong. Your brain filled in gaps with reasonable guesses, borrowed details from other birthdays, invented specifics that feel true but never happened. Every time you remember something, you change it slightly. Memory is not playback. It is creative writing based on fragmentary notes. The hippocampus, a seahorse shaped structure deep in your brain, acts as a temporary storage facility for new experiences. When you learn something, the hippocampus holds it for hours or days, replaying the neural pattern over and over, especially during sleep. Gradually, if the memory matters enough, it transfers to the cortex for long term storage. This process, called consolidation, requires time. You cannot rush it. Sleep deprived students who cram all night retain less than those who study moderately and sleep well. The brain needs darkness and rest to solidify what the light and activity taught. Scientists have identified the molecular machinery of memory formation. When neurons fire together repeatedly, a cascade of proteins strengthens the connection between them. Glutamate receptors multiply on the receiving neuron's surface. Structural proteins reshape the synapse itself, making future signals stronger. This process, called long term potentiation, was discovered in the 1970s by Turgay Lumeau and Tim Bliss. They found that brief, high frequency stimulation of neurons in a rabbit's hippocampus created lasting changes in synaptic strength. This was the physical basis of learning, visible under laboratory conditions. But here is the limitation: each meaningful memory requires thousands or millions of these synaptic changes. The memory of a single face involves neurons in your fusiform face area, your emotional amygdala, your language centers that store the person's name, your motor regions that remember how you embrace them. These regions must coordinate their activity across centimeters of brain tissue, timing their signals with millisecond precision. Evolution spent millions of years perfecting this system. We have studied it seriously for perhaps 70 years. The question emerged in the late 20th century: could quantum mechanics explain consciousness and memory? Quantum physics describes the bizarre behavior of matter at the smallest scales, where particles exist in multiple states simultaneously until observed. Some scientists wondered whether the brain might exploit these quantum effects. Perhaps memory existed not just in synaptic connections, but in quantum states within neurons themselves. Perhaps consciousness emerged from quantum computations happening in microscopic structures called microtubules that form the skeleton of each neuron. This idea attracted physicists and philosophers, but skepticism from neuroscientists. The brain is warm, wet, and chaotic, exactly the conditions that destroy delicate quantum states. Quantum effects require extreme cold or isolation. The inside of a living neuron seemed too messy for quantum phenomena to survive. Yet the question persisted. If quantum mechanics governs the behavior of atoms and molecules, and brains are made of atoms and molecules, then quantum effects must occur somewhere in neural tissue. The real question became, do these quantum effects matter for how memory and consciousness actually work? The 21st century brought new tools. Functional magnetic resonance imaging allowed scientists to watch the living brain in action. Optogenetics gave researchers the ability to control specific neurons with light. Quantum computers began solving problems that classical computers could not touch. These three developments, brain imaging, neural control, and quantum computing, converged in the public imagination to suggest a possibility. If we could map memories, control neurons precisely, and harness quantum mechanics, could we implant memories directly into the brain? Science fiction had explored this concept for decades. Films depicted characters downloading martial arts skills in seconds or implanting entirely false life histories. These stories resonated because they addressed deep anxieties and desires. The anxiety of inadequacy. Everyone else seems to know more. The desire for transformation, becoming someone better without the painful process of change. The fear of manipulation, someone else controlling what you remember and therefore who you are. Memory implantation stories were never really about technology. They were about identity, autonomy, and the shortcuts we wish existed. But what does science actually say? Can quantum mechanics enhance memory? Can we implant knowledge directly into neurons? The answers require understanding what memory truly is, what quantum computing actually does, and why the gap between science fiction and scientific reality remains vast. The journey through this question will take us from the molecular machinery inside a single synapse to the philosophical problem of personal identity. We will examine real breakthroughs in memory research and real limitations in quantum biology. We will explore why some dreams of human enhancement remain perpetually 20 years in the future. The truth about memory implantation is stranger and more interesting than the fiction. It reveals not just the boundaries of current technology, but the nature of consciousness itself. It forces us to ask what we would lose if learning became effortless, if memory became programmable, if the struggle to understand and remember vanished. These questions matter now, before the technology exists, because the conversation about what we should do must precede the ability to do it. Tonight, as you drift towards sleep, your brain will begin its nightly work of memory consolidation. The experiences of your day will replay in your hippocampus, gradually transferring to your cortex for permanent storage. This natural process, refined over millions of years of evolution, remains more sophisticated than anything human engineers have created. Understanding it begins with understanding what memory actually is at the most fundamental level. The neuron is not a simple wire. Under an electron microscope, a single neuron reveals itself as a complex biological machine with branching dendrites that receive signals and a long axon that sends them. Where two neurons meet, they do not touch. A tiny gap called the synapse separates them, measuring only 20 to 40 nanometers across. This gap is where memory physically lives. When an electrical signal reaches the end of one neuron, it triggers the release of chemical messengers called neurotransmitters. These molecules float across the synaptic gap and bind to receptors on the receiving neuron. If enough receptors activate, the receiving neuron fires its own electrical signal. This process happens trillions of times per second throughout your brain. Memory formation begins with repetition. When you learn a new word or practice a physical skill, specific patterns of neurons fire together. Donald Hebb, a Canadian psychologist, proposed in 1949 that neurons that fire together wire together. This principle, now called Hebbian learning, describes the fundamental rule of neural plasticity. Each time you repeat an action or thought, the synapses involved in that neural pattern become slightly stronger. The neurotransmitter release becomes more efficient. The receiving neuron grows more receptors. The physical connection changes. The molecular cascade of memory consolidation involves dozens of proteins working in precise sequence. When a neuron receives a strong signal, calcium ions flood into the cell. This calcium surge activates enzymes called kinases. These kinases modify existing proteins and trigger the production of new ones. One crucial kinase, called calcium calmodulin dependent protein kinase 2, remains active for hours after the initial signal. It phosphorylates other proteins, adding chemical tags that change their behavior. This creates a molecular memory of the neural activity that persists long after the electrical signal has faded. The SIAMPA receptor plays a central role in synaptic strengthening. These protein channels sit in the receiving neuron's membrane, allowing sodium ions to enter when glutamate binds to them. Weak synapses have few AMPA receptors. Strong learning experiences trigger the insertion of additional AMPA receptors into the synapse. More receptors mean stronger responses to the same amount of neurotransmitter. This is long-term potentiation, the cellular basis of learning. Turge Lomo discovered this phenomenon in 1966 while working in Per Anderson's laboratory in Oslo. They stimulated neurons in rabbit hippocampal slices with brief, high-frequency electrical pulses. Hours later, those same neurons showed enhanced responses to normal stimulation. The synapse had changed permanently. Tim Bliss and Turge Lomo published their groundbreaking work in 1973. They demonstrated that long-term potentiation could last for days or weeks. This was the first clear evidence that memory had a physical basis in synaptic modification. Later research revealed the opposite process: long-term depression. Weak or infrequent stimulation causes AMPA receptors to be removed from the synapse, weakening the connection. Your brain constantly adjusts synaptic strengths up and down, sculpting neural circuits based on experience. The hippocampus serves as the brain's memory indexer. This structure, shaped like a curved seahorse, consists of several regions with distinct functions. The dentate gyrus receives input from the cortex, processing millions of sensory details into unique patterns. The CA3 region stores these patterns temporarily, linking related information together. The CA1 region compares new experiences to stored patterns, detecting novelty and significance. When you experience something worth remembering, the hippocampus coordinates the storage of different aspects across multiple cortical regions. Your visual cortex stores what you saw. Your auditory cortex stores what you heard. Your motor cortex stores how you moved. The hippocampus maintains an index linking these distributed fragments. Sleep is when this indexing becomes permanent. During slow-wave sleep, the hippocampus replays the day's neural patterns. Brain imaging studies show that if you learn to navigate a maze during the day, the same navigation neurons fire during sleep in the same sequence, just faster. This replay happens hundreds of times throughout the night. Each replay strengthens the cortical connections slightly. Gradually, the memory becomes independent of the hippocampus. This explains why damage to the hippocampus prevents new memory formation, but often spares old memories. The old memories have already transferred to the cortex. Henry Malazan, known in scientific literature as patient HM, provided crucial evidence for the hippocampus's role. In 1953, surgeons removed most of his hippocampus to treat severe epilepsy. The surgery stopped his seizures, but left him unable to form new long-term memories. He could hold a conversation, but minutes after you left the room, he would forget meeting you. His childhood memories remained intact. His procedural memory, how to tie shoes, ride a bicycle, still worked. But he could not remember what happened yesterday or even 5 minutes ago. Brenda Milner studied him for decades at McGill University. Her work with HM established that memory is not one thing, but multiple systems supported by different brain structures. Forgetting is not a failure of memory. It is an essential feature. Your brain receives approximately 11 million bits of sensory information per second. Your conscious mind can process perhaps 50 bits per second. If you remembered everything, you would drown in irrelevant details. Forgetting allows generalization. When you learn that one hot stove burns, you need to forget the specific details, the exact temperature, the pattern of the tiles, and remember the general principle that hot stoves burn. This requires actively weakening synapses that encode irrelevant details while strengthening synapses that encode useful patterns. The consolidation process is selective. Emotional experiences consolidate more strongly than neutral ones. The amygdala, an almond shaped structure adjacent to the hippocampus, labels experiences with emotional significance. When the amygdala activates, it releases norepinephrine and other stress hormones that enhance hippocampal activity. This is why you remember your first kiss or a car accident more vividly than what you ate for lunch last Tuesday. Evolution shaped memory to prioritize survival relevant information. Threats and opportunities matter more than routine details. Reconsolidation reveals memory's fundamental instability. Kareem Nader at McGill University demonstrated that each time you recall a memory, it becomes temporarily unstable. For several hours after retrieval, the memory must be reconsolidated, stabilized again through protein synthesis. During this window, the memory can be modified, enhanced, or weakened. This explains why psychotherapy works. Talking about traumatic memories in a safe context allows those memories to reconsolidate with reduced emotional intensity. It also explains why eyewitness testimony proves unreliable. Each time witnesses recount their story, especially under leading questioning, they modify the memory slightly. Elizabeth Loftus demonstrated this experimentally in the 1970s. She showed subjects videos of car accidents, then asked questions with subtle suggestions embedded. Subjects who were asked about the car's speed when it smashed into the other car estimated higher speeds than those asked when it hit the other car. A week later, subjects in the smashed condition were more likely to falsely remember seeing broken glass that was not in the video. The language used during questioning had altered their memory. This research revolutionized legal understanding of eyewitness reliability and revealed memory's constructive nature. Memory is not retrieval of stored data, it is reconstruction from distributed fragments. Each time you remember your grandmother's kitchen, your brain assembles a simulation from sensory fragments, emotional associations, and semantic knowledge. It fills in missing details with plausible guesses based on your general knowledge of kitchens. The resulting memory feels like accurate playback, but contains numerous inaccuracies and inventions. You experience it as true because your brain presents the reconstruction as a unified, coherent scene. This is why 10 siblings can have 10 different memories of the same childhood event, each equally confident in their version. The protein synthesis requirement for consolidation provides a window for intervention. Drugs that block protein synthesis administered shortly after learning can prevent memory formation. Researchers have explored this for treating post traumatic stress disorder. The idea is to have patients recall their traumatic memory, then administer a drug during the reconsolidation window, potentially weakening the emotional component while preserving the factual memory. This remains experimental and controversial. The ethical questions are profound. Even traumatic memories contribute to identity. Who are you if you selectively erase your past? Memory systems are multiple and distinct. Declarative memory, facts and events you can consciously recall, depends on the hippocampus and cortex. Procedural memory, skills and habits, involves the basal ganglia and cerebellum. Emotional memory, conditioned fear responses, centers on the amygdala. Working memory, holding information temporarily in mind, activates the prefrontal cortex. Each system has different cellular mechanisms, different time courses, different vulnerabilities to damage. Patient HM could learn new motor skills despite having no conscious memory of practicing them. His procedural memory system remained intact. The discovery of neurogenesis, birth of new neurons in the adult brain, challenged the old dogma that brain cells do not regenerate. In the 1990s, Elizabeth Gould and others demonstrated that the hippocampus produces thousands of new neurons daily. These newborn neurons integrate into existing circuits, potentially contributing to new memory formation. Stress suppresses neurogenesis. Exercise enhances it. The functional role of adult neurogenesis remains debated, but it suggests that the memory system retains plasticity throughout life. This plasticity means memory can be enhanced through training, but also means it remains vulnerable. Sleep deprivation devastates memory consolidation. One night of poor sleep impairs the hippocampus's ability to encode new memories. Chronic sleep deprivation causes measurable shrinkage of the hippocampus. Stress hormones like cortisol, helpful in short bursts, damage hippocampal neurons when chronically elevated. Depression, anxiety, and chronic stress all correlate with memory problems because they damage the very structures that support memory formation. The natural memory system is remarkable and fragile. It evolved to serve survival in ancestral environments, not to memorize phone numbers or master calculus. Its strengths, emotional prioritization, gist extraction, flexible reconstruction, are exactly what modern life often demands we overcome. We want perfect recall of arbitrary facts. We want immunity to emotional bias. We want memories that do not fade or distort. These desires drive the dream of artificial memory enhancement, but they also reveal a misunderstanding of what memory is for. Memory is not data storage, it is identity construction, pattern recognition, and meaning making. The imperfections are not bugs, they are features that make us adaptive, creative, and human. Quantum mechanics describes reality at the smallest scales, where the rules that govern everyday objects break down completely. A coin on your desk is either heads or tails. A quantum coin exists in both states simultaneously until you look at it. This is superposition, the defining weirdness of quantum systems. Particles behave like waves spread across space. They tunnel through barriers that classical physics says they cannot cross. Two particles become entangled, so measuring one instantly affects the other regardless of distance. Albert Einstein called this spooky action at a distance and spent years trying to prove it impossible. He was wrong. Quantum mechanics is not intuitive, but it is correct. The quantum computer exploits these strange properties to process information in fundamentally new ways. A classical computer bit is either 0 or 1. A quantum bit, called a qubit, exists in a superposition of 0 and 1 simultaneously. Two classical bits have four possible states, but can only be in one at a time: 0, 0, 1, 1, 0, or 1, 1. Two qubits exist in all four states simultaneously. Three qubits represent eight states at once. The number of simultaneous states grows exponentially. 50 qubits represent more states than there are atoms in the solar system. This exponential advantage is why quantum computers can solve certain problems that classical computers never could. But quantum computing is not magic. It is mathematics under different rules. Most importantly, quantum computers are not universally faster than classical computers. They excel at specific types of problems: factoring large numbers, searching unsorted databases, simulating quantum systems. These tasks show exponential quantum speedup, but adding two numbers or sorting a list shows no quantum advantage. The popular misconception is that quantum computers do everything faster. The reality is they do a few things exponentially faster, and most things no faster at all. Google announced quantum supremacy in 2019. Their Sycamore processor with 53 qubits solved a specific problem in 200 seconds that would take the world's fastest supercomputer 10,000 years. The problem itself had no practical application. It was designed specifically to showcase quantum advantage. Critics argued about whether the comparison was fair and whether supremacy was the right term. But the achievement was real. A quantum device had crossed the threshold where classical computers could no longer keep up, even on an artificial benchmark. IBM has taken a different approach, focusing on modular quantum systems that users can access through the cloud. Their quantum processors contain dozens of qubits, arranged in specific connectivity patterns. Universities and companies worldwide run quantum algorithms on IBM's hardware, exploring applications in chemistry, optimization, and machine learning. The systems remain deeply imperfect. Qubits are extraordinarily fragile. Environmental noise, vibrations, temperature fluctuations, stray electromagnetic fields disrupts their quantum state within microseconds. This is decoherence, the collapse of superposition into classical definite states. Maintaining quantum coherence requires extreme conditions. Most quantum computers operate at temperatures near absolute zero, colder than outer space. They are housed in elaborate cryogenic refrigerators with multiple thermal stages, each one isolating the qubits further from environmental heat. The engineering challenges are immense. A single qubit might require an entire cubic meter of equipment to support it. Scaling to thousands or millions of qubits means building refrigeration systems the size of buildings. Error correction compounds the scaling problem. Quantum states are so fragile that errors occur constantly. A physical qubit might maintain coherence for a fraction of a second at best. Quantum error correction requires encoding each logical qubit across many physical qubits. Current estimates suggest you need roughly 1,000 physical qubits to create one error corrected logical qubit. To run useful algorithms, you might need millions of physical qubits. Current systems have tens to hundreds. The gap between present and useful quantum computing spans several orders of magnitude. The algorithms that show quantum advantage are highly specific. Shor's algorithm can factor large numbers exponentially faster than any known classical algorithm. This threatens current encryption systems, which rely on the difficulty of factoring. But factoring numbers has nothing to do with memory or consciousness. Grover's algorithm searches an unsorted database in time proportional to the square root of the database size. This is faster than classical search, but only quadratically, not exponentially. And again, searching databases is not thinking or remembering. Quantum simulation is perhaps the most promising application. Richard Feynman proposed quantum computers in the 1980s, specifically to simulate quantum systems. Molecules and materials are quantum objects. Their electrons exist in superposition. Their energy levels obey quantum rules. Simulating even a medium sized molecule on a classical computer requires approximations that limit accuracy. A quantum computer could simulate molecular behavior directly, potentially revolutionizing drug discovery and materials science. But here is the critical distinction. Quantum computers manipulate quantum states according to quantum mechanical laws. Brains are biological organs operating at body temperature in wet, noisy environments. The quantum states that quantum computers exploit are extraordinarily fragile and require isolation from exactly the conditions that exist inside a living brain. A quantum computer works because you cool it to near absolute zero and shield it from all environmental noise. A neuron operates at 37 degrees Celsius, bathed in a soup of ions and molecules constantly bombarded by thermal fluctuations. The idea that the brain might use quantum computing arose from consciousness's apparent mystery. Consciousness feels unified, yet the brain is a network of billions of separate neurons. Consciousness seems to involve instant global integration of information, yet neural signals travel at meters per second, not light speed. Some researchers wondered whether quantum effects might explain these puzzling features. Roger Penrose, a mathematical physicist, proposed in his book The Emperor's New Mind that consciousness arises from quantum computations occurring in microtubules inside neurons. Microtubules are protein structures that form the cell's skeleton. They are hollow tubes made of tubulin proteins arranged in a lattice. Penrose and anesthesiologist Stuart Hameroff proposed that electrons in these tubulin proteins could exist in quantum superposition, performing quantum computations that classical neural firing could not achieve. They called this orchestrated objective reduction, or ORCOR. The theory suggests that consciousness emerges when quantum superpositions in microtubules reach a threshold and collapse, creating discrete moments of conscious experience. Most neuroscientists reject Orcon for several reasons. First, the brain's warm, wet conditions should destroy quantum coherence in picoseconds, trillionths of a second. The theory requires coherence to persist for milliseconds, millions of times longer than physics predicts. Second, anesthetics affect consciousness by binding to various receptors, not by disrupting microtubules specifically. Third, organisms without microtubules show complex behavior and arguably consciousness. Single celled organisms navigate their environment effectively without quantum computing. Max Tegmark, a physicist at MIT, calculated the decoherence time for quantum states in brain microtubules. His analysis suggested coherence would last approximately 10 to the powers of minus 13 seconds. Conscious thought operates on timescales of tenths of a second or longer, 10 orders of magnitude slower. For quantum effects in microtubules to matter for consciousness, they would need to somehow survive in conditions that quantum physics says should destroy them almost instantly. This requires new physics, not just new biology. The debate highlights a common pattern in pseudoscientific thinking. Quantum mechanics is mysterious. Therefore, one must explain the other. This is the fallacy of false equivalence. Both consciousness and quantum mechanics are poorly understood in some respects, but that does not make them related. Consciousness might be explained entirely by classical neural processes we do not yet fully understand. Quantum mechanics might be completely irrelevant to brain function. Recent research has found some quantum effects in biological systems. Photosynthesis uses quantum coherence to transfer energy efficiently. Birds might use quantum entanglement in their magnetic sense. These findings show that biology can exploit quantum effects under specific circumstances. But these are isolated processes in specialized structures, not general computational principles. A light harvesting complex in a plant is optimized by evolution to maintain quantum coherence for the picoseconds needed for energy transfer. This is far from consciousness requiring quantum computing. The jump from quantum computers exists to brains use quantum computing to we can implant quantum memories involves multiple unjustified leaps. First, quantum computers manipulate information in ways completely different from classical computers. They do not store memories or run programs in any sense a neuroscientist would recognize. Second, even if brains somehow used quantum effects, that would not mean we could engineer those effects for memory implantation. Evolution spent billions of years optimizing biological systems. We cannot simply add quantum features to an existing brain any more than you can add flight to a fish. Third, memory is not computation in the sense that either classical or quantum computers perform. Computers process inputs according to algorithms and produce outputs. Memory is reconstruction, pattern completion, context dependent retrieval. A computer gives the same output for the same input every time. Your memory of an event changes based on your current mood, recent experiences, and the way someone asks about it. These are fundamentally different types of information processing. The quantum computing revolution is real and important. Within decades, quantum computers might design better batteries, discover new drugs, optimize logistics networks, and break current encryption systems. But they will do this by solving specific mathematical problems faster, not by mimicking or enhancing human cognition. The path from a quantum processor in a laboratory refrigerator to a memory implanted in a living brain does not exist. It is not that we lack the engineering to build it. The physics that makes quantum computing possible is the same physics that makes quantum effects impossible in the warm, wet, noisy environment of a living brain. Understanding what quantum computers actually do and what they cannot do is essential for evaluating claims about quantum memory enhancement. The quantum computer is a powerful tool for specific calculations. It is not a magic solution to consciousness, and it is not a pathway to implanting memories. The real breakthroughs in memory research come not from quantum physics, but from understanding the molecular and cellular mechanisms that brains actually use. Those mechanisms, while still incompletely understood, are fundamentally classical. They involve chemicals, proteins, and electrical signals governed by the ordinary laws of chemistry and physics. They are no less remarkable for being classical. The field of quantum biology emerged from observations that should not be possible according to classical physics. In 1977, Graham Fleming and his team discovered that photosynthetic light harvesting complexes transfer energy with near perfect efficiency. The energy absorbed by chlorophyll molecules travels through the protein structure to the reaction center with almost no loss. Classical physics predicted this process should be messy and inefficient, like passing a basketball through a crowd where people randomly deflect it. Instead, the energy moves as if it knows the shortest path. The explanation came decades later. In 2007, researchers used ultra-fast laser spectroscopy to watch energy transfer in real time. They found quantum coherence lasting hundreds of femtoseconds, hundreds of quadrillionths of a second. The excitation exists as a wave-like superposition spread across multiple chlorophyll molecules simultaneously. This quantum spreading allows the energy to explore many paths at once and take the most efficient route. Evolution discovered quantum mechanics billions of years before humans did. But notice the conditions. Photosynthetic complexes are rigid protein structures optimized specifically to protect quantum coherence. The process occurs in picoseconds to femtoseconds, timescales so short that thermal vibrations have not yet disrupted the quantum state. And even with these optimizations, coherence lasts only microseconds at most. Once the energy reaches the reaction center, classical chemistry takes over. The quantum effect is a brief specialized trick for a specific task. Magnetoreception in birds presents another tantalizing case. European robins navigate using Earth's magnetic field, detecting directional changes smaller than the field strength variation caused by nearby metal objects. The proposed mechanism involves a protein called cryptochrome in the bird's retina. When blue light hits cryptochrome, it creates a pair of electrons in an entangled state called a radical pair. Earth's magnetic field affects how this radical pair evolves. The biochemical products depend on the field orientation, potentially creating a visual pattern that overlays the bird's normal vision. Klaus Schulten proposed this radical pair mechanism in 1978. Evidence has accumulated supporting it, but controversies remain. The quantum state must survive for microseconds in the bird's eye while surrounded by moving molecules at body temperature. Some calculations suggest this is impossible. Others argue that the protein structure shields the radical pair sufficiently. What is clear is that if birds use quantum effects for navigation, it is again a highly specialized structure evolved specifically for that purpose, not a general principle of neural computation. Olfaction, the sense of smell, might involve quantum tunneling according to Luca Turin's controversial theory. The traditional lock and key model says odorant molecules fit into receptor proteins based on their shape. Turin proposed that receptors detect molecular vibrations through quantum tunneling of electrons. Different molecules vibrate at different frequencies. An electron tunneling through the molecule responds to these vibrations, allowing the receptor to distinguish molecules with similar shapes but different vibrations. The theory predicts that molecules with the same shape but different isotopes should smell different because isotopes change vibration frequency. Some experiments support this prediction. Other experiments contradict it. The scientific consensus leans toward the lock and key model being correct, with vibration theory explaining at most a minor contribution. But even if vibration theory were entirely correct, it would show only that one sensory system uses quantum tunneling to distinguish similar molecules. This says nothing about memory, learning, or consciousness. These examples share important features. First, they involve specialized structures evolved specifically to exploit quantum effects. They are not general features of cells or brains. Second, the quantum effects occur on femtosecond to microsecond timescales and involve just a few particles. They are not large-scale quantum computations. Third, the quantum effect enhances or enables a specific function: energy transfer, magnetic sensing, molecular detection, but does not constitute thinking or memory. The brain operates on completely different scales. Conscious thought unfolds over hundreds of milliseconds. Memory formation requires hours. These are 9 to 12 orders of magnitude slower than the quantum effects observed in photosynthesis or radical pairs. For quantum effects to matter for cognition, they must somehow survive in a noisy biological environment for timescales millions of times longer than quantum biology has demonstrated anywhere. Temperature is the fundamental challenge. Quantum superposition is fragile because it requires isolation from environmental interactions. Each interaction with the environment measures the quantum state, collapsing superposition into a definite classical state. Temperature represents the random motion of molecules. At 37 degrees Celsius, molecules move frantically, colliding billions of times per second. Each collision is a measurement that destroys quantum coherence. Photosynthesis works because the protein structure is rigid and the process is fast. The energy transfer completes before molecular vibrations can disrupt it. Bird magnetoreception works because the radical pair is shielded inside a protein and only needs to survive for microseconds. But neurons fire on millisecond timescales. Memories consolidate over hours. These processes are far too slow and involve far too many molecules to maintain quantum coherence. Consider the numbers. A single synapse contains approximately 1,000 neurotransmitter vesicles. Each vesicle contains thousands of neurotransmitter molecules. When the synapse fires, dozens of vesicles release their contents, millions of molecules flooding the synaptic gap. These molecules bind to thousands of receptors, each receptor a large protein complex that changes shape when activated. The receptor shape change opens ion channels, allowing millions of sodium or calcium ions to flow through. This is wet, noisy, classical chemistry with trillions of molecular interactions. Where in this process would quantum superposition survive? The OR theory attempts to answer this by proposing that quantum computations occur inside microtubules, isolated from the cytoplasm's chaos. But microtubules are not isolated. They are constantly interacting with motor proteins that walk along them, transporting cargo. Tubulin subunits constantly detach and reattach as the microtubule grows and shrinks. The microtubule interior is filled with water molecules, ions, and other small molecules. It is not the pristine quantum environment that quantum computing requires. Max Tegmark calculated that quantum superposition in a microtubule tubulin dimer should decohere in 10 to the power of negative 13 seconds at brain temperature. This is 100 femtoseconds, far shorter than the milliseconds to seconds that consciousness operates on. Stuart Hameroff has argued that Tegmark's calculation is too pessimistic, that the microtubule structure provides more shielding than the model assumes. But even if you multiply Tegmark's estimate by 1 million, you still fall far short of the timescales cognition requires. Some researchers propose that the brain does not maintain quantum coherence but exploits quantum effects at the moment of their collapse. The quantum superposition exists for femtoseconds, but its collapse influences which synapses fire, steering neural activity in ways that classical physics cannot. This is a more modest claim, but still faces problems. The number of molecules involved in neural firing is so large that quantum uncertainties average out. Quantum randomness at the molecular level becomes classical statistical predictability at the cellular level. The comparison to quantum computers is instructive. Quantum computers require near absolute zero temperature to function. They are shielded inside multiple layers of insulation. They operate for microseconds before errors accumulate. Even with these extreme precautions, quantum coherence is fragile and difficult to maintain. The brain operates at body temperature with no shielding, processing information continuously for decades. These conditions are incompatible with quantum computing as we understand it. Perhaps the brain uses quantum effects we have not yet discovered. This is possible, but not a basis for confident claims. Science progresses by explaining the unknown in terms of the known, not by invoking mysteries to explain mysteries. We know that classical neural processes, synaptic transmission, long term potentiation, network dynamics, can explain a great deal of brain function. Invoking quantum effects should be a last resort when classical explanations fail completely. More fundamentally, the question is whether quantum effects would help. Quantum computers excel at specific calculations, factoring, database search, quantum simulation. These capabilities do not map onto cognitive functions. Memory is not database search. Learning is not factoring. Thinking is not quantum simulation. Even if the brain somehow maintained quantum coherence, it is unclear what computational advantage this would provide for the things brains actually do. The appeal of quantum consciousness theories lies partly in their mystique. Consciousness feels mysterious. Quantum mechanics is famously counterintuitive. Linking them creates a satisfying sense that one deep mystery explains another. But this is intellectual aesthetics, not evidence. The actual evidence shows that quantum effects in biology are rare, specialized, fragile, and brief. They occur in specific structures, under specific conditions, for specific purposes. They are not general features of wet, warm, complex biological systems. The gap between quantum biology and quantum consciousness is vast. Demonstrating quantum coherence in a light harvesting complex does not suggest quantum coherence in neural networks. The mechanisms are different, the timescales are different, the functions are different, the evolutionary contexts are different. Each claim must stand on its own evidence. The evidence for quantum effects in cognition remains weak to non existent. This matters for evaluating memory implantation claims. If someone proposes quantum memory enhancement, ask about the mechanism. What specific quantum effect is being exploited? How is it maintained at body temperature? What evolutionary evidence suggests the brain uses this effect? How would manipulating it improve memory without disrupting other quantum processes in the body? These questions usually reveal that quantum is being used as a vague signifier of advanced technology rather than a concrete physical mechanism. Quantum biology is a legitimate field revealing how evolution sometimes exploits quantum effects for specific functions. Quantum consciousness is speculation that has not been supported by evidence and faces severe theoretical obstacles. Quantum memory implantation requires both quantum consciousness to be true and a technology to manipulate it that does not exist even in concept. The chain of unsupported claims grows longer at each step, making the final proposal vanishingly unlikely. The brain's actual memory mechanisms, synaptic plasticity, protein synthesis, neural network dynamics are classical processes. They are remarkable and still incompletely understood. But they are not mysterious in the sense of requiring new physics. They are complex in the sense of involving millions of interacting components. Complexity is not the same as quantum mechanics. Understanding and potentially enhancing memory will come from molecular biology and neuroscience, not from quantum physics. The quantum dream is a distraction from the harder work of understanding how the brain actually functions. Philip K. Dick published the short story We Can Remember It For You Wholesale in 1966. The protagonist pays a company to implant false memories of a vacation to Mars. During the procedure, technicians discover he actually went to Mars as a secret agent, but had those real memories erased. The story questions whether implanted and real memories are distinguishable, whether identity persists when memories change. Paul Verhoeven adapted it loosely into Total Recall in 1990, emphasizing action over philosophy, but keeping the central question: how do you know your memories are real? The Matrix trilogy took memory implantation further. Neo downloads martial arts skills in seconds. His brain receives a program, and suddenly he knows Kung Fu. The film visualizes this as code scrolling across his vision. Then, I know Kung Fu. The scene lasts perhaps 30 seconds on screen. Learning that would take years occurs instantaneously. This is the fantasy at its purest. Knowledge without effort, skill without practice, transformation without growth. Black Mirror episode The Entire History of You explored memory from a different angle. People have implants that record everything they see and hear. They can replay any memory with perfect fidelity. This eliminates false memories and convenient forgetting. The protagonist uses his implant to obsessively review interactions with his wife. The technology that promised perfect recall destroys his relationships and his sanity. The episode suggests that forgetting is not a flaw but a necessity for psychological health. Another Black Mirror episode, Be Right Back, uses recorded memories to resurrect the dead. A woman loses her partner in an accident. A service collects all his social media posts, messages, and recorded conversations. An artificial intelligence trained on this data impersonates him, first through text, then voice calls, finally inhabiting an android body. But the replica is hollow. It mimics surface behaviors without inner life. The episode demonstrates that memory is not data. Even perfect records of someone's words and actions do not capture who they were. These stories resonate because they address real anxieties. We feel inadequate, aware of how much we do not know. We fear losing memories to age or injury. We wonder if our memories are accurate or if we have been deceived. We question whether we are the same person we were 10 years ago if our memories have changed. Memory implantation fiction gives concrete form to these abstract concerns. The stories also express desires. Who has not wished to acquire a skill instantly? Learning requires tedious repetition, frustration, failure, time. If you could download fluency in a language, mastery of an instrument, expertise in a field, you could become anyone you want to be. This fantasy appeals especially to those who feel trapped by their current limitations: students struggling in school, adults wanting career changes, anyone who has given up on a dream because learning seemed too hard. The military applications appear in many versions. Create super soldiers by implanting combat skills and eliminating hesitation to kill. Upload mission parameters directly into soldiers' brains. Erase traumatic memories to prevent post traumatic stress disorder. These ideas reflect cultural anxieties about dehumanization in warfare and the treatment of veterans. They ask whether it is ethical to modify soldiers' minds, whether the person who returns from war is the same person who left. Educational applications seem more benign, but raise similar questions. If you could implant knowledge, should expensive universities exist? If anyone could have a medical degree uploaded, what happens to the years doctors spend training? If expertise becomes cheap and instant, how does society value knowledge? The stories reveal that instant learning would not just save time, it would fundamentally alter social structures built around education, apprenticeship, and credentialing. The earliest versions of this fantasy predate science fiction. Medieval grimoires described rituals for instant knowledge. Faust makes a deal with the devil for unlimited knowledge and experience. These myths recognize that shortcuts to wisdom carry a price. The alchemist seeking instant gold goes mad. The sorcerer who gains forbidden knowledge loses his soul. The lesson is consistent. Knowledge without effort is dangerous because effort builds character, judgment, and wisdom along with skill. Subliminal learning tapes promised a modern version of this fantasy. Beginning in the 1950s, companies sold audio tapes claiming to teach languages, improve memory, or change behavior through subliminal messages below conscious awareness. You would listen during sleep, and information would supposedly enter your subconscious, bypassing the conscious mind's limitations. Millions of people bought these tapes despite zero scientific evidence they worked. Sleep learning research began in earnest in the 1950s. Charles Simon and William Emmons conducted rigorous studies at Bell Labs. They played recorded information to sleeping subjects, then tested recall upon waking. The results were clear. Subjects learned nothing while genuinely asleep. If they recalled anything, EEG recordings showed they had been partially awake when the information played. True sleep provided zero learning benefit. The research was published in 1956, but did little to stop the industry selling sleep learning products. The fantasy persists because people want to believe. If sleep is one-third of life, using it for learning seems efficient. If consciousness limits learning through attention and effort, bypassing consciousness seems clever. But the research is unambiguous. Sleep does not absorb new information. It consolidates information learned while awake. The hippocampus, replays recent experiences, strengthening the synaptic connections formed during waking learning. You cannot skip the waking learning phase. Memory editing appears in eternal sunshine of the spotless mind. Ex lovers pay to have memories of each other erased. The procedure works by having the client recall targeted memories, while technicians map the activated neural patterns and disrupt them. As the protagonist's memories of his relationship are deleted, he changes his mind. He wants to keep them even though they hurt. The film argues that painful memories are part of who we are. Erasing them erases yourself. Inception inverted the concept. Instead of extracting memories, the characters implant ideas. They enter someone's dreams and plant a thought that will seem like their own realization. The film's complexity comes from nested dream layers and the question of whose reality is genuine. But the core concept, again, involves bypassing conscious resistance to change someone's mind. The emotional climax comes when the protagonist realizes he implanted guilt in his wife's mind, causing her death. The film warns that changing someone's memories against their will is a form of murder. These stories share common themes. Memory implantation technology promises shortcuts, but delivers unintended consequences. Characters who use it lose their identity, damage relationships, or cause harm. The technology reveals that memory is not separate from self. Changing memories changes the person. The stories are warnings disguised as entertainment. They say, be careful what you wish for, but they are fiction, not forecasting. Science fiction authors create scenarios to explore ethical questions, not to predict technology. Total Recall does not suggest memory implantation is coming soon, any more than Star Wars suggests faster than light travel is imminent. The technologies are plot devices, enabling exploration of identity, reality, and consciousness. Critiquing them as unrealistic misses the point. They are not meant to be realistic. The problem arises when people take science fiction as science. When someone claims to work on quantum memory implantation, they are borrowing science fiction's aesthetic. The white lab coats, the futuristic equipment, the jargon that sounds scientific, these are props from movies, not elements of research. Real neuroscience looks less exciting. Mice in mazes, neurons in petri dishes, hours of tedious measurement. Fiction is more compelling than reality, which is why it is easier to sell impossible products than to explain what research actually achieves. Real memory research rarely matches fiction's drama. Scientists spend years teaching rats to press levers, trying to understand what neural changes occur during simple learning. They publish papers with titles like Calcium Dynamics in Dendritic Spines During Long-Term Potentiation that summarize thousands of hours of work on questions most people find tedious. This is how science actually progresses, through incremental advances on narrow questions, not through paradigm-shattering breakthroughs every week. The gap between fiction and reality creates unrealistic expectations. People imagine that if we can sequence genomes and build quantum computers, we should be able to implant memories. But technological progress is uneven. We can do some things that seem miraculous, communicate instantly across continents, carry supercomputers in our pockets, while other things that seem simpler remain impossible. We can sequence DNA, but cannot cure most genetic diseases. We can build quantum computers, but cannot make them useful for most tasks. We can image the living brain, but cannot read thoughts. The lesson from memory implantation fiction is not that the technology is coming. The lesson is that we should be careful assuming shortcuts work. Every story about memory implantation is ultimately about the value of lived experience. The process of learning matters more than the possession of knowledge. The struggle to remember teaches patience. The pain of loss teaches empathy. Eliminating these struggles would not improve us, it would diminish us. Fiction explores the implications of technology before it exists so we can think through the consequences, but it does not promise or predict the technology's arrival. Elizabeth Loftus showed research subjects a video of a car accident. Afterward, she asked half the subjects, how fast were the cars going when they hit each other? She asked the other half, how fast were the cars going when they smashed into each other? The subjects who heard smashed estimated higher speeds, 41 miles per hour, versus 34 miles per hour. 1 week later, she asked all subjects if they remembered seeing broken glass in the accident. There was no broken glass in the video. But 32% of subjects in the smashed condition reported seeing broken glass, compared to 14% in the hit condition. A single word in a question had created false memories in 1/3 of subjects. This research, published in 1974, revolutionized legal understanding of eyewitness testimony. For centuries, courts treated eyewitnesses as reliable sources. If someone clearly remembered seeing the defendant at the crime scene, that testimony could convict. Loftus demonstrated that memory is far more malleable than the legal system assumed. Leading questions, suggestive language, and misleading information can all create false memories that feel completely real to the person experiencing them. The misinformation effect occurs when information presented after an event alters memory of the event. In another classic study, Loftus showed subjects slides of a car approaching an intersection. Some subjects saw a stop sign, others saw a yield sign. Afterward, subjects answered questions that either matched reality or contradicted it. For example, subjects who saw a stop sign might be asked about the yield sign. Later memory tests showed that subjects exposed to contradictory information often remembered the false detail instead of what they actually saw. Post event information had overwritten the original memory. The implications are profound. Every time witnesses discuss an event, they risk contaminating each other's memories. When police officers ask leading questions during interviews, they may inadvertently create the very evidence they seek. When news media reports details about a crime, they implant information that witnesses will later misremember as their own observations. Memory is not a video recording that can be replayed. It is a story constantly being rewritten. Loftus pushed further. Could entirely false memories be created, not just alterations of real events? In the 1990s, she conducted the Lost in the Mall studies. Researchers asked adult subjects to recall childhood events, including one fabricated story about being lost in a shopping mall and rescued by an elderly person. Family members corroborated the real events, but not the false one. Initially, subjects denied remembering being lost. Over several interviews, researchers gently encouraged them to try harder to remember. By the end, about 25% of subjects claimed to remember the false event, adding sensory details, emotions, and narrative elements that researchers had never mentioned. These were not vague feelings that maybe something had happened. Subjects described specific visual details: the color of the rescuer's flannel shirt, the layout of the mall, their mother's reaction. They experienced the full phenomenology of genuine memory, visual imagery, emotional resonance, the conviction of truth. The false memories felt indistinguishable from real ones because the brain generates both through the same reconstruction process. False memories are not lies. The person experiencing them genuinely believes they are real. The research emerged during the recovered memory controversy of the 1980s and 90s. Some therapists use techniques like hypnosis, guided imagery, and suggestive questioning to help clients recover supposedly repressed memories of childhood abuse. Many clients developed detailed memories of horrific abuse they had previously forgotten. People were imprisoned based on testimony from recovered memories. Loftus and other memory researchers testified that these recovered memories might be false memories created by suggestive therapeutic techniques. The backlash was severe. Therapists accused researchers of protecting abusers. Survivors groups accused them of denying real trauma. Death threats arrived. Loftus's office was vandalized. The controversy became vicious because the stakes were so high. If recovered memories were real, failing to believe them meant protecting abusers. If they were false, believing them meant destroying innocent people's lives. The scientific consensus eventually emerged. Memories can be forgotten and later remembered. But memories recovered through suggestive techniques are unreliable. Hypnosis does not enhance memory accuracy. It enhances confidence in both true and false memories. Repeatedly imagining a scenario can create a false memory of experiencing it. The therapeutic techniques meant to uncover truth were actually manufacturing fiction. The legal system slowly adapted. Many jurisdictions now view hypnotically refreshed testimony with skepticism. Expert witnesses testify about memory's malleability. Juries receive instructions about eyewitness reliability's limits. But change has been slow. The intuitive belief that memory works like a video recorder persists despite decades of contradictory evidence. Memory suggestibility has practical implications beyond the courtroom. Advertising exploits it. If commercials repeatedly associate a product with positive emotions, people later misremember having positive experiences with that product. Political campaigns use it. Repeatedly suggesting an opponent did something wrong makes people misremember seeing evidence of it. Misinformation spreads, and people later remember false stories as if they saw them happen. Children are especially vulnerable to false memory creation. Their developing brains are more plastic, and they are more susceptible to adult suggestion. Researchers have implanted false memories in children of being kissed by a Bugs Bunny character at Disneyland. Impossible because Bugs Bunny is a Warner Brothers character. Children have testified about satanic ritual abuse that investigations proved never occurred. The combination of suggestive interviewing, social pressure, and childhood suggestibility created elaborate false narratives. But adults are not immune. Braun and colleagues conducted a study where subjects viewed Disneyland advertisements showing Bugs Bunny. Afterward, about 16% of subjects falsely remembered meeting Bugs Bunny at Disneyland as children. The advertisement had implanted the memory. This has advertising implications. Companies can potentially create false memories of positive experiences with their brands. The mechanisms of false memory creation parallel normal memory formation. When you imagine an event vividly, you activate similar neural patterns to those activated by actually experiencing the event. With repetition, these neural patterns strengthen through the same synaptic mechanisms that consolidate real memories. The brain cannot inherently distinguish between patterns created by imagination and those created by perception. Both feel real because both are real neural activity. Source monitoring is the process of determining whether a memory originated from perception, imagination, or someone else's testimony. This process is prone to errors. You might misattribute something you imagined to something you saw. You might remember something told to you as your own observation. You might confuse dreams with reality. Source monitoring depends on contextual details, where you were, who you were with, what it looked like. These details fade faster than the core memory, leaving you certain something happened, but uncertain of the source. Emotion enhances both real and false memories. Emotional experiences consolidate more strongly due to stress hormone effects on the amygdala and hippocampus. But emotion also makes people more susceptible to false memories. If creating a false memory involves strong emotional imagery, that emotional engagement strengthens the false memory. This is why traumatic false memories, when created through therapy, feel especially real. The emotional intensity seems like evidence of authenticity, but it is not. Sleep can strengthen false memories. If you form a false memory during the day, sleep consolidation will strengthen it just like a real memory. The hippocampus replays false memories during sleep, transferring them to cortex for long term storage. Sleep does not distinguish true from false. It consolidates whatever neural patterns exist. This means false memories become more deeply embedded over time. The research on false memory creation is not about memory implantation technology. It is about social influence, suggestive questioning, imagination, and expectation. No brain scans, no chemicals, no devices. Just words and social pressure. This makes it more disturbing, not less. We do not need advanced technology to manipulate memory. We are already doing it constantly through conversation, media, advertising, and interrogation. The practical takeaway is to be skeptical of your own memories, especially for events you have discussed repeatedly or that others have told you about. Treat vivid emotional memories with care. They may feel certain but still be wrong. Recognize that confidence and accuracy are poorly correlated. The memories you are most sure about may be the most distorted because you have recalled them most often, giving them more opportunities to change. Elizabeth Loftus's research demonstrates that memory is not testimony from the past. It is imagination based on fragmentary evidence. We are all unreliable narrators of our own lives. This is not a defect to be corrected with technology. It is the nature of a system optimized for prediction and adaptation, not for archival accuracy. The brain cares more about what might happen next than what happened before. Memory serves the future more than the past. Understanding this helps set realistic expectations for memory enhancement. The foundation is already unreliable. Building on it with technology will not create perfect recall. It will create different, possibly worse, forms of distortion. Susumu Tonegawa won the Nobel Prize in Physiology or Medicine in 1987 for discovering how the immune system generates antibody diversity. But his later work on memory earned him a different kind of recognition. In 2012, his laboratory at MIT published research that shocked neuroscientists and captured public imagination. They had implanted a false memory in a mouse. This was not metaphor or exaggeration. They had literally made a mouse remember something that never happened. The technique is called optogenetics. It combines genetic engineering with fiber optics to control specific neurons using light. The process begins by inserting a gene from light sensitive algae into targeted neurons. This gene codes for a protein called channel rhodopsin that sits in the cell membrane. When blue light hits channel rhodopsin, it opens, allowing ions to flow through and causing the neuron to fire. By implanting a fiber optic cable into the mouse's brain, researchers can shine light on specific neurons and activate them at will. The precision is remarkable. Traditional methods of brain stimulation, electrical currents, magnetic fields, chemicals, affect all nearby neurons indiscriminately. Optogenetics can activate only neurons that express channel rhodopsin. By controlling which neurons get the gene, researchers control which neurons light can activate. This specificity enables experiments impossible with earlier techniques. Tanagawa's team wanted to test whether specific memories are stored in specific groups of neurons. They used mice because mouse brains are small enough to access with current technology while still sharing fundamental memory mechanisms with human brains. The experiment had three phases. In the first phase, they let a mouse explore a chamber while a genetic marker tagged neurons active during exploration. These active neurons received the channel rhodopsin gene. These were the neurons encoding the memory of that chamber. In the second phase, they placed the mouse in a completely different chamber with different walls, different floor, different smell. While the mouse was in this second chamber, they did two things simultaneously. They gave the mouse mild foot shocks, unpleasant but not harmful, to create a fear memory, and they shone light through the implanted fiber optic cable, artificially activating the neurons tagged in the first chamber. This forced the mouse's brain to activate the memory of chamber 1 while experiencing shocks in chamber 2. The third phase tested what the mouse remembered. They placed the mouse back in chamber 1. A normal mouse would explore this chamber calmly, since nothing bad had ever happened there. But Tonegawa's mouse froze in fear. It remembered chamber 1 as dangerous, even though it had never been shocked there. The mouse had a false memory. It believed chamber 1 was the location of the foot shocks, when actually the shocks occurred in chamber 2. The neuroscience community reacted with amazement and appropriate skepticism. The experiment was replicated. It worked. This was genuine memory manipulation at the cellular level. Headlines proclaimed, "Scientists implant false memories in mice," and drew comparisons to total recall. But the comparison reveals how far reality trails fiction. The implanted memory was not complex. It was a simple fear association. This place is dangerous. The mouse did not gain new skills or knowledge. It did not remember events that never occurred. It associated fear with the wrong location. The limitations are crucial. First, the memory had to already exist. Researchers could not create a memory from nothing. They tagged neurons active during actual exploration of chamber 1. They reactivated those neurons in a different context, creating a false association, but the building blocks came from real experience. Second, the manipulation required surgical implantation of a fiber optic cable. Third, it required genetic modification to insert channel rhodopsin genes. Fourth, the mice were specially bred and raised in controlled laboratory conditions. And fifth, the false memory was extremely simple compared to any human memory. Steve Ramirez and Shu Liu, the postdoctoral researchers who conducted the experiment under Tanagawa's supervision, were careful to emphasize these limitations. In interviews, they stressed that implanting complex memories in humans was far beyond current capabilities, but they also expressed optimism that understanding memory at the cellular level might eventually lead to treatments for conditions like post traumatic stress disorder or Alzheimer's disease. The technique has advanced since 2012. Researchers have created positive associations, making mice prefer locations where they experienced optogenetically induced pleasure. They have reactivated specific memories and modified them during reconsolidation. They have demonstrated that memories are not stored in a single location, but distributed across multiple brain regions. Each advance clarifies how memory works at the neural level. But each advance also reveals new complexity. In 2015, Tanagawa's lab showed that memories exist in two forms simultaneously. One form depends on strengthened synapses and supports recall. The other form involves potential for synaptic strengthening and supports recognition. This means a single memory is not a single thing. It is multiple representations serving different functions. Manipulating memory requires addressing all these representations simultaneously. The engram, the physical trace of a memory, proved more distributed than expected. A memory of a location involves neurons in the hippocampus, but also neurons in the sensory cortex processing visual and tactile information, neurons in the motor cortex involved in navigation, and neurons in the amygdala if any emotion attached to the experience. These distributed populations must coordinate their activity. Reactivating the hippocampal component alone is insufficient. The full memory requires synchronized activation across multiple brain regions. Channel rhodopsin is not the only optogenetic tool. Halarodopsin, another light sensitive protein, inhibits neurons when activated by yellow light. This allows researchers to silence specific neurons, testing their necessity for a behavior or memory. Archarodopsin allows inhibition with green light. These tools enable both activation and inhibition with temporal precision measured in milliseconds. Researchers can test not just which neurons are involved in a process, but when their activity matters. The technique has limits. Fiber optic implants are invasive. They cause tissue damage. They cannot reach deep brain structures without crossing other regions. The light scatters as it travels through tissue, limiting precision. Only a small volume of brain tissue can be illuminated effectively. For mice whose brains weigh half a gram, this is manageable. For humans whose brains weigh 1.4 kilograms, the scaling problem is severe. The viral vectors that deliver channel rhodopsin genes to neurons are imperfect. They infect some, but not all, targeted neurons. They sometimes infect neurons outside the target region. The expression level varies. Some neurons produce abundant channel rhodopsin, while others produce little. This variability limits experimental precision and would be unacceptable in clinical applications. The immune system poses another challenge. In mice bred for research, immune responses to viral vectors are manageable. In humans, immune reactions to foreign proteins like channel rhodopsin could cause inflammation, damaging the very neurons you are trying to control. Long-term safety data does not exist. No one knows what happens when light-sensitive proteins remain in human neurons for years or decades. Temporal precision is both a strength and a limitation. Optogenetics can activate neurons with millisecond timing, matching the speed of natural neural activity. But memory operates on much slower timescales. A single experience involves neural activity over seconds or minutes. That activity must then consolidate over hours through protein synthesis. To implant a memory optogenetically, you would need to maintain specific patterns of activation across multiple brain regions for extended periods, while avoiding disruption of ongoing brain function. This is far beyond current capabilities. The mouse experiments demonstrate a principle. Memories have physical substrates that can be manipulated, but the gulf between principle and practice is vast. Demonstrating that you can create a simple fear association in a mouse brain prepared by surgery and genetic modification does not suggest you can implant complex knowledge in a human brain. The mouse experiments are valuable for understanding memory mechanisms, not as steps toward memory implantation technology. The ethical questions begin even at the mouse level. Should we manipulate animal memories for research? The mice experience real fear from false memories. They cannot consent. We justify animal research by requiring that potential benefits outweigh harms and that alternatives are unavailable. These standards permit current optogenetic memory research in animals, but they would not permit human memory manipulation without extraordinary justification. Some human applications might meet ethical standards. Treating post traumatic stress disorder by weakening traumatic memories during reconsolidation could reduce suffering. Strengthening memories in early Alzheimer's disease could preserve identity and independence, but these therapeutic applications are far from current capabilities. The technique that works in mice requires brain surgery and viral gene delivery. No patient would accept these risks for memory enhancement. Only severe disease justifies such invasive procedures. The optogenetic revolution in neuroscience is real and important. It has enabled discoveries about circuit function, behavior, and cognition impossible with earlier techniques. Laboratories worldwide use optogenetics to probe how specific neurons contribute to specific functions. The technique has revealed surprising complexity in neural circuits, contradicted old assumptions, and opened new research directions. This is genuine scientific progress, but progress in understanding is not progress toward manipulation. Knowing how a system works does not mean you can control it. Understanding how weather systems generate hurricanes does not let you prevent hurricanes. Mapping the neural circuits of memory does not mean you can safely alter those circuits in living humans. The knowledge gap is closing slowly. The engineering gap remains enormous. And the ethical gap, the conversation about whether we should even if we could, has barely begun. The lesson from optogenetics is subtle. Memory has a physical basis. That basis can be manipulated in controlled laboratory conditions, but the manipulation requires invasive procedures, produces limited effects, and works only in organisms bred specifically for such research. The gap between this and the science fiction fantasy of downloading skills or implanting knowledge is not a gap of a few years or a few innovations. It is a gap of fundamental principles, practical impossibilities, and ethical prohibitions that together make memory implantation, in the science fiction sense, a perpetual mirage, receding faster than we approach it. The human brain contains approximately 80 to 6 billion neurons. Each neuron connects to roughly 7,000 other neurons on average. This creates approximately 600 trillion synapses, 600,000 billion connection points where neural communication occurs. A single memory, even a simple one, like recognizing your friend's face, involves coordinated activity across millions of these synapses distributed throughout multiple brain regions. This is not a metaphor or an approximation. These are the actual numbers that any memory implantation technology must confront. Compare this to current brain computer interfaces. The most advanced research systems implant electrode arrays with a few thousand recording sites. Neuralink's latest device contains 1,024 electrodes. The Utah array, used in research for decades, has 96 electrodes. These are impressive achievements requiring microsurgical precision and advanced materials. But 1,000 electrodes monitoring a brain with 600 trillion synapses is like trying to understand a conversation in a stadium by listening to 3 random people out of 600 million attendees. The numbers become worse when you consider what implanting a memory requires. Recording neural activity is easier than controlling it. To implant a memory, you must activate specific neurons in specific patterns at specific times across multiple brain regions. This is not measuring, this is writing. The precision requirements explode. You need not just to detect activity, but to induce it accurately enough to mimic natural memory formation without disrupting existing neural function. Natural memory formation illustrates the complexity. When you learn a new fact, neurons fire in patterns determined by what you are experiencing. These firing patterns trigger calcium influx into thousands of neurons. The calcium activates kinases in those neurons. The kinases phosphorylate proteins. Some of these proteins travel to the nucleus and activate genes. The genes produce new proteins that strengthen synapses. This process occurs simultaneously in millions of neurons across multiple brain regions. The timing coordination is exquisite. Neurons in visual cortex, language areas, and hippocampus must fire in precise sequences measured in milliseconds. To artificially create this process, you would need to identify which neurons should fire, when they should fire, in what sequence, and how strongly. Then you would need a way to make them fire in that pattern without disrupting the ongoing brain activity that keeps you conscious and alive. Current technology cannot even identify all the relevant neurons, let alone control them with the required precision. The mapping problem is fundamental. Each person's brain is wired differently. The visual cortex is in roughly the same location in everyone, but the specific neurons encoding your grandmother's face are unique to you. They formed through your specific life experiences. Another person's neurons encoding their grandmother are in similar but not identical locations, connected to different sets of neurons with different synaptic strengths. There is no standard template. You cannot create a memory file and upload it to any brain like installing software on any computer. This is radically different from computer memory. A computer has standardized memory addresses. Writing the value 1 into address 0x100 does the same thing in every computer of the same architecture. But writing a memory into a human brain requires knowing that person's unique neural architecture. You would need a complete connectome, a map showing every neuron and every synapse. The project to map the connectome of a single cubic millimeter of mouse brain has taken years and is not complete. 1 cubic millimeter. The human brain is approximately 1.3 million cubic millimeter. The C. elegans worm has exactly 302 neurons. Researchers fully mapped its connectome in 1986. This was an extraordinary achievement, requiring electron microscopy and painstaking reconstruction of neural connections from thousands of thin slices. The complete wiring diagram has enabled decades of research into how neural circuits produce behavior. But C. elegans is a worm with behaviors like moving forward, moving backward, and avoiding toxins. Humans have behaviors slightly more complex. Our 300 trillion synapses encode vastly richer behavioral repertoires. Even if you somehow obtained a complete connectome of a living human brain, knowing the wiring does not tell you the functional properties. Synapses have different strengths. Some are excitatory, increasing the likelihood the receiving neuron will fire. Others are inhibitory, decreasing firing probability. The strength of each synapse depends on its history of activity. Two synapses connecting the same pair of neurons can have completely different strengths. The connectome shows structure but not function. You need both to understand how information is encoded. Synaptic strength changes constantly through learning and experience. The connectome you mapped yesterday is obsolete today. The brain's plasticity, which makes learning possible, makes static maps insufficient. You would need real-time mapping of synaptic strengths across the entire brain. No technology comes remotely close to this capability. High-resolution imaging methods like electron microscopy require dead tissue. They kill what they measure. Functional magnetic resonance imaging can measure brain activity in living people, but with terrible resolution. fMRI measures blood flow, which correlates with neural activity, but lags behind it by seconds. The spatial resolution is roughly 1 cubic millimeter, about 100,000 neurons. You cannot distinguish individual neurons, let alone measure individual synapses. fMRI tells you which brain regions are active, not what those regions are encoding or how they are encoding it. Calcium imaging, used in animal research, has better resolution. By genetically engineering neurons to produce fluorescent proteins that glow when calcium enters the cell, Researchers can watch thousands of individual neurons simultaneously. But this requires genetic modification, works only near the brain surface, and cannot image the entire brain at once. It is invaluable for research, but not scalable to human clinical applications. The writing problem is harder than the reading problem. Optogenetics can activate individual neurons in genetically modified animals, but making neurons fire is not the same as making them encode information. Memory encoding requires specific patterns of activity in specific sequences across distributed populations. Randomly activating neurons will not create meaningful memories. It will create noise or seizures. The information capacity question looms large. How much information does a single memory contain? This is unknown because memory is not digital. It is distributed patterns of analog synaptic strengths. A rough estimate: if each synapse can exist in one of 10 strength states, and a memory involves changes to 1 million synapses, the memory contains about 3 megabytes of information. But this is meaningless because the information is not in a format any external device can read or write. The brain's internal encoding is unique to each person and inaccessible to external observation. The timing problem compounds all others. Neurons fire on millisecond timescales. Synaptic proteins change on minute to hour timescales. Memory consolidation requires hours to days. To implant a memory, you must coordinate all these timescales correctly. Fast artificial activation of neurons will not produce the slow protein synthesis required for consolidation. You cannot simply speed up the process because the speeds are determined by chemical reaction rates. Even if technology advanced to allow mapping and stimulating individual neurons, you face the integration problem. New memories must integrate with existing knowledge. If you implant knowledge of calculus, that knowledge must connect to existing mathematical knowledge, to language areas for understanding calculus terms, to motor areas for writing equations, to emotional areas so calculus problems feel meaningful rather than meaningless symbol manipulation. Creating these connections naturally takes years of learning. Artificially creating them requires modifying millions of existing synapses, not just creating new ones. The verification problem is perhaps most severe. How do you know you successfully implanted a memory? The person's self report is unreliable. They might confabulate or experience false confidence. Behavioral testing might show they can perform a task, but procedural memory is different from declarative memory. They might be able to do something without knowing how they do it or being able to explain it. True memory implantation would require both skill and understanding, both procedure and declaration. Testing this requires extensive evaluation that might itself alter the memory through reconsolidation. The safety problem cannot be overstated. The brain is not modular. Regions connect extensively. Attempting to modify one region will affect others through cascading neural activity. The risk of unintended consequences is enormous. Seizures, personality changes, loss of existing memories, psychological trauma, all are possible outcomes of invasive brain manipulation. Clinical trials would require demonstrating safety in thousands of subjects before broader use. But who volunteers for experimental brain manipulation that might erase their existing memories or personality? The reversibility problem presents an ethical barrier. If you implant a memory that turns out to be harmful, can you remove it? Probably not. Once synaptic changes occur and consolidate, they become part of the brain's structure. Memory suppression therapies for PTSD do not erase memories. They modify how the brain accesses them. Truly erasing a specific memory while preserving everything else requires precision beyond foreseeable technology. Any memory implantation would be permanent for better or worse. These are not temporary obstacles awaiting a few innovations. They are fundamental challenges arising from the brain's basic architecture. 600 trillion synapses distributed across 1.3 million cubic millimeters of tissue that is unique in each person and constantly changing. This is not an engineering challenge like building a faster computer or a more efficient solar panel. Those problems involve known physics and scalable manufacturing. Memory implantation requires simultaneously solving dozens of problems that individually would take decades, then integrating those solutions into a system that does not kill or harm the person. The gulf between current technology and science fiction memory implantation is not a gulf of years or even decades. It may be a gulf that can never be crossed because the brain's complexity may be irreducible. Some problems have no shortcut. Understanding a brain may require living through a life. Creating a memory may require experiencing events. The engineering problem may be unsolvable, not because engineers lack skill, but because the problem itself is ill posed. Memory is not data to be transferred, but structure to be grown through experience. You cannot implant growth any more than you can implant childhood. Some processes admit no shortcuts. Nanotechnology promises to manipulate matter at the molecular scale. The vision includes microscopic machines that travel through blood vessels, cross the blood brain barrier, and interface directly with individual neurons. These nanobots would read neural activity with unprecedented precision and potentially write new neural patterns, creating or modifying memories. This is the technological hope that might overcome the engineering limitations described previously. It is worth examining seriously to understand both its promise and its profound difficulties. The blood brain barrier poses the first obstacle. This selective barrier protects the brain from toxins, pathogens, and immune cells circulating in the bloodstream. The barrier consists of specialized endothelial cells that line brain blood vessels. Unlike blood vessels elsewhere in the body, brain capillaries have tight junctions where cells seal together, preventing most molecules from crossing. Only small, lipid soluble molecules, or those with specific transporters, can enter the brain naturally. This protects neural tissue but also prevents drug delivery. Nanoparticles face this same barrier. A nanobot in the bloodstream cannot simply float into brain tissue. It must either be small enough to cross the barrier directly, roughly 5 nanometers or smaller, or hijack existing transport mechanisms. At 5 nanometers, you have space for perhaps a few hundred atoms. This is not large enough for any complex device. A single ribosome, the molecular machine that builds proteins in cells, is 20 to 30 nanometers. A nanobot smaller than a ribosome cannot carry computation, power, communication, and manipulation capabilities. Hijacking transport mechanisms is possible in principle. Transferrin receptors transport iron across the blood brain barrier. Coating nanoparticles with transferrin might allow them to piggyback through. This works experimentally but with low efficiency. Most nanoparticles are still blocked. Those that enter are scattered throughout the brain, not targeted to specific regions. Controlling their distribution precisely enough to manipulate specific memories is far beyond current capabilities. Temporarily disrupting the blood brain barrier is another approach. Focused ultrasound can open the barrier in specific regions for hours, allowing nanoparticle entry. This has been tested for drug delivery in brain tumors, but it causes inflammation and carries risks of bleeding. Using it to deliver memory manipulating nanobots to healthy brains would require demonstrating extraordinary safety. The regulatory barriers would be immense, even if the technical barriers were overcome. Assume, for argument's sake, that nanobots reach brain tissue. They must then interface with neurons. A neuron is approximately 20 micrometers in diameter, 20,000 nanometers. A 100 nanometer nanobot is 500 times smaller than the neuron it must monitor or manipulate. This is like a person trying to repair a 50-story building from inside while being the size of a fingernail. You are too small to affect large structures and too large to manipulate molecular scale components. Recording neural activity requires detecting voltage changes across the cell membrane. The voltage change during an action potential is roughly 1/10 of a volt across a membrane 7 nanometers thick. Detecting this from outside the cell requires extraordinary sensitivity. The nanobot must get close enough to measure small voltage changes without being crushed by the cell membrane's constant motion or swept away by fluid flow in the extracellular space. Stimulating neural activity requires injecting current or releasing chemicals to depolarize the cell membrane. The nanobot needs a power source to generate current or storage for chemicals to release. Batteries at the nanoscale have minimal capacity. Chemical storage is limited by the nanobot's volume. A 100 nanometer sphere has a volume of roughly half a million cubic nanometers. If entirely filled with neurotransmitter molecules, it could hold perhaps 10,000 molecules. A single synaptic vesicle releases several thousand neurotransmitter molecules per firing event. The nanobot could stimulate a few firings at most before exhausting its payload. Power is a severe constraint. Batteries store energy in chemical bonds, with energy density limited by chemistry. The smallest batteries are lithium ion, with energy density around 1 megajoule per kilogram. A typical LED requires milliwatts. A nanobot would exhaust its battery in microseconds if powering anything comparable to current electronics. Wireless power transmission via electromagnetic fields works, but requires large antennas relative to the nanobot size and deposits energy as heat. Heat dissipation is critical. The brain tolerates only narrow temperature ranges. Even a 1 degree increase can impair function. A few degrees can cause damage. Billions of nanobots, each dissipating heat, would raise brain temperature unless heat removal mechanisms existed. The brain's blood flow removes metabolic heat, but it is optimized for neurons' energy use. Adding substantial heat from nanobots would require augmented cooling, which means either increased blood flow, altering brain function, or some other heat removal mechanism not present in current designs. Communication between nanobots and external controllers requires radio or acoustic signals. Radio waves penetrate tissue poorly at high frequencies where antennas can be small. Low frequencies require large antennas. Acoustic signals work, but are slow and low bandwidth. Coordinating billions of nanobots in real time to implement a complex memory would require communication bandwidth that the brain's tissues cannot support without significant signal loss and interference. Even assuming all these challenges are solved, nanobots must navigate to specific neurons. The brain is not a uniform tissue. It contains hundreds of distinct regions with different cell types. A memory involves specific subsets of neurons in multiple regions. Nanobots must somehow identify the correct neurons, say, neurons in your visual cortex encoding your grandmother's face, and target only those. But neurons encoding specific information are not labeled. They are functionally defined by their activity patterns. You cannot identify them without first observing the brain during the relevant experience. This creates a temporal impossibility. To implant a memory of meeting someone, nanobots must activate neurons that would naturally activate during such a meeting. But those neurons are defined by their activity during actual meetings. You cannot know which neurons to activate unless you have recorded activity during a similar experience. To implant novel knowledge, information you have never encountered, you must activate neurons in patterns they have never exhibited. Predicting these patterns requires understanding the brain's encoding scheme. We do not have this understanding. The immune system presents another barrier. Any foreign object in the body triggers immune responses. Nanoparticles are recognized as foreign and attacked by macrophages and other immune cells. Coating nanoparticles with biological molecules can reduce immune detection temporarily, but long-term presence still triggers inflammation. Chronic inflammation damages tissue. For nanobots to remain in the brain for extended periods, they would need either immunosuppressant coverage, which increases infection risk, or biocompatible materials that somehow evade immune detection indefinitely. We do not have such materials. Biodegradation is an alternative. Nanobots could be designed to dissolve after completing their function, but this creates a one-time use scenario. To maintain or modify memories, you would need repeated nanobot injections. Each injection carries risks. The degradation products must be non-toxic and clearable by the body. Testing the long-term safety of degraded nanobot components would require decades of study. Current nanoparticle research focuses on drug delivery, imaging, and diagnostics, Gold nanoparticles visualize tumors. Lipid nanoparticles deliver mRNA vaccines. Iron oxide nanoparticles enhance MRI contrast. These are passive or simple applications, delivering chemicals or absorbing light. Active manipulation of neural circuits requires capabilities orders of magnitude more sophisticated. The gap between delivering a drug and implanting a memory is comparable to the gap between delivering mail and teleportation. Timeline projections are revealing. Researchers began serious discussion of medical nanorobots in the 1980s. Eric Drexler's book, Engines of Creation, outlined molecular manufacturing possibilities. Nearly 40 years later, we have simple nanoparticles, but no autonomous nanobots. Progress has been slower than optimistic predictions suggested because the challenges are deeper than initially appreciated. Optimism is easy when you do not yet understand the problems. Making predictions about future technology is hazardous. Experts had been wrong before. Powered flight was declared impossible shortly before the Wright brothers flew. Nuclear energy was dismissed as fantasy years before it was achieved. But these examples involved overcoming single key obstacles. Memory implantation via nanotechnology requires overcoming dozens of independent obstacles simultaneously: blood brain barrier crossing, navigation, targeting, recording, stimulation, power, communication, heat dissipation, immune evasion, and biocompatibility. Each one is unsolved. Solving all of them requires not one breakthrough but many, some of which may contradict each other. More fundamentally, even perfect nanobots cannot overcome the information problem. They could potentially record and stimulate individual neurons. But what patterns should they create to encode a specific memory? This requires understanding the brain's neural code. That code is not universal. It is learned through development and experience. Your brain's code is different from mine. Even with perfect hardware, we lack the software, the knowledge of what patterns implement what memories. The comparison to genetic engineering is instructive. We can now edit genes with precision using CRISPR. But editing genes does not let us design organisms from scratch. We can make small modifications and observe effects. Designing a new organism requires understanding how genes interact to produce complex traits. That understanding remains incomplete despite decades of research. Similarly, even if we could edit neurons with precision, we could not design memories without understanding how neural patterns encode information. The hardware solution does not solve the information problem. Nanotechnology will advance. Researchers will develop better nanoparticles for drug delivery and imaging. Monitoring individual neurons may become possible in limited contexts. But the vision of nanobots, implanting complex memories into human brains, runs into not one or two obstacles, but dozens of fundamental barriers. Each barrier could take decades to address. Many may be unsolvable with any foreseeable technology. The timeline for memory implantation, if it is ever possible, is measured not in years, but in generations. And even that assumes problems prove solvable that may turn out to be fundamentally intractable. John Locke argued in 1694 that personal identity consists of continuity of consciousness, particularly continuity of memory. You are the same person you were 10 years ago because you remember being that person. If all your memories vanished, replaced with someone else's memories, you would be that other person in an important sense. Your body might remain the same, but the person inhabiting it would be different. This memory theory of identity has influenced philosophy, psychology, and law for 3 centuries. But Locke's theory faces immediate objections. You do not remember most of your past. Your first day of school, your 10th birthday, thousands of ordinary days, all forgotten, yet you are still the same person who lived through them. Locke responded that identity requires only indirect memory chains. You remember yesterday, and yesterday you remembered the day before, forming an unbroken chain to childhood even if you cannot currently recall childhood directly. But this creates problems. If the chain breaks, through amnesia or brain injury, does personal identity break too? Thomas Reed proposed the brave officer paradox in 1785. A boy is flogged for stealing apples. The boy grows into a brave officer who captures an enemy flag and remembers the flogging. The officer becomes an elderly general who remembers capturing the flag but has forgotten the flogging. By Locke's theory, the general is the same person as the officer, who is the same person as the boy. But the general is not the same person as the boy, because he does not remember being the boy. Identity should be transitive. If A equals B and B equals C, then A equals C. Locke's theory violates transitivity. Derek Parfit, a 20th century philosopher, pushed these thought experiments further. Suppose we could scan your brain, destroy the original, and create an exact copy on Mars with all your memories. Is the Mars person you, or merely someone who thinks they are you? Most people's intuition says it is not you because the original died. But now suppose we create the copy without destroying the original. Two people both have your memories and both claim to be you. They cannot both be you because they are numerically distinct. Or is personal identity dissolved by duplication? Parfit argued that what matters for survival is not identity, but psychological continuity. The Mars copy preserves your memories, personality, values, and goals. That is what you care about, not whether some metaphysical essence called identity transfers. If you anticipate the Mars copy's experiences the way you anticipate tomorrow's experiences, then in the relevant sense you survive. Identity is not an all or nothing metaphysical fact, but a matter of degree based on psychological connections. Now apply this to memory implantation. Suppose technology allowed implanting complete sets of memories. You could pay to receive all the memories of a concert pianist. After the procedure, you remember decades of practice, thousands of performances, the joy of music. These memories feel absolutely real because they are real neural patterns, indistinguishable from naturally formed memories. But they are not your memories. You did not live through them. Are you now partially the pianist? Has your identity been diluted or enhanced? The question becomes more troubling if memories conflict. You remember graduating from medical school and also remember never attending college. You remember your mother as kind and also remember her as abusive. Your brain cannot simultaneously believe contradictions, so it must choose which memories to accept as real. The choosing process will itself alter both sets of memories. The implanted memories will begin to feel false, or the original memories will be reinterpreted to accommodate the new ones. Either way, your sense of personal history becomes fragmented and unreliable. Memory is not just information storage, it is the narrative structure that gives life meaning. You understand your current self as the result of past experiences. Your childhood shaped your values. Your education enabled your career. Your relationships formed your personality. This narrative continuity provides stability and direction. Implanted memories would disrupt this narrative. They would insert events that did not cause your current state, creating logical contradictions in your self understanding. Consider skills versus episodic memories. If you could implant the skill of playing piano without the memories of learning, you would have procedural knowledge without declarative knowledge. You could play but not remember practicing. This is similar to what happens in some amnesia cases. Patients retain skills learned before the amnesia but do not remember learning them. The skill feels alien, as if your hands know something your mind does not. This dissociation between knowing how and knowing that creates an unsettling sense of being estranged from your own abilities. Now consider implanting only episodic memories without skills. You remember playing Carnegie Hall but cannot actually play piano. The memory feels real, but your inability to perform contradicts it. This is actually what happens with false memories. You remember events that your skills and knowledge contradict. Elizabeth Loftus's subjects remember seeing broken glass but lack the visual expertise to distinguish real from false visual memories. Implanted memories without corresponding skills would create similar contradictions, undermining confidence in all your memories. The emotional component of memory is inseparable from its content. Your grandmother's kitchen matters because you loved your grandmother. The memory carries emotional weight that influences your current emotional life. If you implanted someone else's memory of their grandmother's kitchen, You would have the visual details, but not the emotional associations. The memory would feel hollow, like remembering a place in a movie rather than a place you lived. To implant a truly functional memory, but emotions are not information. They are physiological states involving hormones, neurotransmitters, and body feedback. Can you implant a physiological state that occurred decades ago? This seems conceptually confused. The ship of Theseus paradox applies directly. The ship sails for years. Gradually, every plank is replaced. Is it still the same ship? If you collect all the original planks and rebuild them into a ship, which ship is the original? Applied to memory. If you replace your memories one by one with implanted ones, at what point do you stop being you? After 10% replacement? 50%? When the last original memory vanishes? There is no principled answer because personal identity is not a binary property, but a network of overlapping connections. Buddhist philosophy denies persistent self altogether. The self is an illusion created by the flow of mental states. Each moment brings a new configuration of thoughts, sensations, and memories. There is no unchanging essence. What we call identity is just a convenient fiction for tracking the continuity of a particular body and mental stream. From this view, memory implantation changes nothing fundamental. Every moment you are already a different person. Implanted memories are just another set of mental states arising and passing. But most people do not experience identity this way. We feel like persisting selves. We make plans assuming we will exist tomorrow to benefit from them. We hold people responsible for past actions, assuming they are the same person who committed them. Legal systems depend on personal identity. You can be punished only for crimes you committed, which requires you being the same person as the criminal. Memory implantation threatens these intuitions and institutions. Responsibility becomes incoherent if memories determine identity. If you implant criminal memories, are you responsible for those crimes? Obviously not. You did not commit them even though you remember committing them. But this shows that memory is insufficient for identity. Something else, actual causal participation in events, matters too. Yet Locke's theory and common intuition both suggest memory is central to identity. The conflict is unresolved in philosophy and would become acute in practice if memory manipulation were possible. The value of authenticity emerges here. Even perfect replicas lack something original experiences have. A memory of climbing Everest that you earned through effort and danger has a quality absent from an implanted memory of the same climb. The quality is not in the memory content, but in the causal history. The memory exists because you did the thing. Implanted memories lack this causal connection. They are simulacra, copies without originals. Some argue that authenticity does not matter. If two experiences are subjectively identical, they have equal value. A perfectly realistic virtual reality vacation is as valuable as a real vacation because the pleasure and memories are the same. But this assumes experience value is entirely subjective. Many people value authentic experiences specifically because they are real, not because of any subjective difference. The knowledge that an experience is authentic changes its meaning even if the subjective quality is identical. Robert Nozick's experience machine thought experiment makes this vivid. You can plug into a machine that gives you any experiences you want. You will feel like you are climbing mountains, writing novels, falling in love, whatever you choose. The experiences feel completely real. Should you plug in? Most people say no. They want to actually do things, not just experience doing them. This suggests we value authentic engagement with reality beyond the subjective feel of our experiences. Memory implantation is a partial experience machine. You get the memories without the experiences. For people who value authenticity, implanted memories would feel hollow regardless of their subjective realism. For people who value only subjective states, implanted memories might be acceptable or even preferable. Why endure years of difficult learning when you can have the skill and memories instantly? This reveals a fundamental values divide. Memory implantation technology would force society to confront what we value about human life and growth. The narrative self model in psychology suggests that identity is a story you tell about yourself. This story incorporates memories but also interprets them, selects which memories to emphasize, and creates coherence by smoothing over contradictions. The story changes over time as you reinterpret your past from your current perspective. Implanted memories would be foreign elements in this narrative. You would struggle to integrate them coherently because they do not connect to the rest of your story. The narrative self would reject them as fictional, even if they feel subjectively real. Children provide an instructive case. A young child has few memories and minimal narrative self, yet we consider them a person with identity. As they grow, they acquire memories and narrative structure, but we do not say they become a person gradually. They were a person from the start. This suggests memory is not constitutive of personhood, but rather a way persons experience their continuity over time. Implanting memories would not create or destroy persons, but would disrupt how persons understand their own existence. The question remains, if technology could perfectly implant memories indistinguishable from natural ones, would using it be wise? The philosophical analysis suggests caution. Memory is too entangled with identity, responsibility, authenticity, and narrative self understanding to be manipulated casually. Even if technology advanced to make it possible, the conceptual and ethical problems would remain. These are not engineering challenges to be solved, but fundamental questions about what it means to be human, what we value, and what kinds of transformations should be resisted even if they become technically feasible. Kim Peek was born in 1951 with brain abnormalities, including an absent corpus callosum, the bundle of fibers connecting the brain's two hemispheres. He also had an enlarged cerebellum and other structural differences. These abnormalities came with extraordinary abilities. By age 3, he was memorizing books. By adulthood, he had memorized roughly 12,000 books covering history, literature, geography, music, and dozens of other subjects. He could read 2 pages simultaneously, one with each eye, and recall the content with near perfect accuracy decades later. Barry Morrow met Peake in 1984 and was so impressed that he wrote the screenplay for Rain Man, loosely basing the character Raymond on Peake's abilities. Dustin Hoffman portrayed Raymond as having exceptional memory and mathematical abilities alongside severe social and communication impairments. The film brought Savant syndrome into public consciousness. After the film's success, Peake traveled extensively giving demonstrations of his memory. He could tell you what day of the week any date fell on, quote, entire books, recite detailed historical facts about thousands of topics. But Peake could not perform many tasks most people find simple. He could not button his shirt. He had difficulty with abstract reasoning. His social interactions were awkward. He needed his father's assistance for basic daily tasks. His extraordinary memory came packaged with significant disabilities. This is the pattern in Savant syndrome. Exceptional abilities in narrow domains coexist with impairments in other areas. The brain seems to compensate for deficits in some regions by overdeveloping others. Daniel Tammet presents a different savant profile. He has high functioning autism and synesthesia. His senses blend so that numbers have colors, shapes, and textures. He can perform extraordinary calculations mentally by manipulating these visual spatial representations. He learned Icelandic in 1 week well enough to give a television interview. He recited pi to 22,514 digits from memory, taking 5 hours and 9 minutes. Unlike many savants, Tammet can articulate his cognitive processes. Numbers, he says, appear in his mind as landscapes he explores. Tammet describes the number 377 as ugly, while 5 is thunder. This synesthetic experience seems to provide memory aids. Rather than remembering abstract symbols, he remembers rich sensory experiences associated with each number. His calculation abilities emerge from pattern recognition in these sensory landscapes. When asked what 9,700 divided by 63 equals, he visualizes the shapes and sees that the answer is 154. Stephen Wiltshire can draw detailed cityscapes from memory after viewing them once. He was flown over Rome in a helicopter for 45 minutes. then drew a detailed panoramic view covering several square meters. The drawing included accurate proportions, correct numbers of windows on buildings, proper architectural details. Similar demonstrations with London, New York, Tokyo, and other cities produced equally accurate results. His visual memory is photographically precise for architectural details, while his memory in other domains is unremarkable. The neurological basis of savant abilities remains incompletely understood. Autopsies on deceased savants show various abnormalities: enlarged hippocampus in some cases, frontal lobe damage in others, absent corpus callosum in Peake's case. The diversity of brain abnormalities associated with savant syndrome suggests there is no single mechanism. Rather, damage or developmental differences in some brain regions somehow lead to overdevelopment of specific abilities, though how and why is unclear. Daryl Treffert, a psychiatrist who studied savants for decades, proposed that savant abilities represent normally dormant capacities that emerge when inhibitory brain circuits are damaged. The left hemisphere normally suppresses certain right hemisphere abilities. When left hemisphere function is impaired, right hemisphere abilities, pattern recognition, visual spatial processing, rote memory, can flourish. This is speculative, but explains why savant abilities often emerge after left hemisphere damage from stroke or injury. Acquired savant syndrome provides evidence for this theory. Orlando Sorrell was hit in the head by a baseball at age 10. After recovering, he could recall the weather and what he did on every day since the accident. Derek Amato dove into a shallow pool, hitting his head. After recovering, he could play piano fluently, despite no prior training. These cases suggest that brain injury can sometimes unlock abilities that were latent but suppressed. The abilities are not created by the injury, but released from inhibition. Alan Snyder at the University of Sydney attempted to temporarily create savant like abilities in normal people using transcranial magnetic stimulation. By inhibiting left anterior temporal lobe function, some subjects showed enhanced drawing ability or improved proofreading performance. The effects were subtle and temporary. This research suggests that savant abilities might not require special neural hardware, but rather a shift in how existing hardware is utilized. However, the research is controversial, and replication attempts have produced mixed results. The cost of savant abilities is crucial. Kim Peake's extraordinary memory came with significant cognitive and social impairments. He needed constant care. His abilities, while remarkable, did not translate into independent living. Stephen Wiltshire's artistic abilities coexist with autism. Daniel Tammet is high functioning, but describes the difficulty of sensory overload and social interaction. The brain appears to have fixed resources. Exceptional development in one domain often requires underdevelopment in others. This is not a necessary trade off. Some people have excellent memories alongside strong social skills and practical abilities. But in savant syndrome, the pattern is clear. Extreme abilities come with corresponding deficits. This suggests that the brain's normal architecture balances multiple demands: memory, reasoning, social cognition, motor control, and executive function all compete for neural resources. Typical development distributes resources broadly. Savant development concentrates resources narrowly. The question for memory enhancement is whether you can gain savant like memory without the associated impairments. The evidence suggests no. Savant abilities emerge from atypical brain development or damage, not from adding capacity to a normal brain. Artificially creating savant abilities in a normally developed brain would likely require disrupting the normal balance, causing impairments in other domains. Hyperthymesia is extreme autobiographical memory without the typical savant profile. Jill Price remembers every day of her life from age 14 onward with extraordinary detail. Given a date, she can tell you what day of the week it was, what she did, what news events occurred, even trivial details like what she ate for lunch. But this ability is not an asset. She describes it as a burden. Trivial memories flood her consciousness constantly. She cannot forget embarrassing moments or painful experiences. Her memories replay involuntarily, making it difficult to focus on the present. Price and other hyperthymetic individuals perform normally on standard memory tests. Their enhanced memory is specific to autobiographical events, not general facts or skills. Brain imaging shows no obvious structural abnormalities. Their obsessive thinking patterns and difficulty moving past events suggest their extreme memory may be closer to obsessive compulsive disorder than to Savant syndrome. The inability to forget is as disabling as the inability to remember. Solomon Cherishevsky, studied by Russian psychologist Alexander Luria in the mid 20th century, had virtually unlimited memory capacity. He could memorize long lists of numbers, words, or nonsense syllables and recall them perfectly years later, but his memory caused problems. He could not forget irrelevant details. When reading, every word evokes such rich associations that he struggled to follow the narrative. Abstract thinking was difficult because abstract concepts triggered floods of specific memories that obscured the abstract pattern. Cherishevsky used synesthesia as a memory technique, similar to Tammet. Each number and letter had colors, sounds, and textures. To remember a list, he would mentally walk down a street placing items at specific locations, creating a visual narrative. This method of loci technique is used by memory athletes worldwide. But for Cherishevsky, it was not a technique, but his native mode of cognition. Information poured in constantly, overwhelming his ability to process it meaningfully. These cases reveal that perfect memory is dysfunctional. The brain needs to forget. Forgetting eliminates irrelevant details, allowing generalization. It reduces interference from old information when learning new information. It weakens painful memories over time, enabling psychological healing. Without forgetting, the mind drowns in detail. Every memory is equally vivid and equally accessible, making it impossible to prioritize or find relevant information efficiently. Memory champions at the World Memory Champions demonstrate that normal people can train to exceptional levels. Competitors memorize decks of cards in under 30 seconds, lists of hundreds of random digits, faces, and names of dozens of strangers. But these are not natural abilities. They are learned skills using deliberate techniques practiced for thousands of hours. They are athletes who train memory like runners train endurance. Joshua Foer, a journalist, trained with memory techniques and won the USA Memory Championship in 2006 after just 1 year of practice. His book, Moonwalking with Einstein, describes the training process. The techniques are not mysterious. They are simply elaborate encoding schemes that transform arbitrary information into memorable visual narratives. Anyone can learn them. But like any skill, mastery requires practice. The competitors are not using different neural mechanisms. They are using standard memory mechanisms more efficiently. The difference between savants and memory champions is illuminating. Savants have atypical brain architecture that produces extraordinary abilities without training, but with associated impairments. Memory champions have typical brain architecture trained to high performance through deliberate practice without associated impairments. This suggests that the path to memory enhancement goes through training, not through modifying brain structure. You can achieve exceptional memory through learning without sacrificing other abilities. The lesson from Savant syndrome is that extreme abilities require trade offs. Nature's experiments in atypical development show that concentrating neural resources produces both gains and losses. The gains are remarkable, but the losses are profound. This is not a limitation of current technology, but a constraint of finite neural resources. The human brain evolved to balance multiple demands, not to maximize any single capability. Disrupting this balance creates disability alongside ability. The dream of enhancing memory without cost runs counter to what Savant syndrome teaches us about how brains actually work. The human brain that struggles to remember where you left your keys is the same brain that, with training, can memorize the order of a shuffled deck of cards in 17 seconds. Johannes Mallow achieved this record in 2015 at the World Memory Championships. The cards flash past, 52 unique items in random order, and afterward, Mallow recites them perfectly. This seems impossible. How can a normal person perform such feats when most of us cannot reliably remember a phone number? The answer is technique, not talent. Memory champions use encoding methods that transform abstract information into vivid, memorable narratives. The most common is the method of loci, also called the memory palace technique. The method is ancient, described in detail in Roman rhetorical texts from 2,000 years ago. Cicero used it to memorize hours long speeches without notes. Medieval scholars used it to memorize entire books. The technique works by exploiting the brain's exceptional spatial memory. Here's how it works: you visualize a familiar location, your house, your commute, your childhood neighborhood. You mentally walk through this location, following a specific route. At specific locations along the route, you place visual images representing the information you want to remember. To memorize a shopping list, you might visualize milk spilling down your front steps, a banana perched on your mailbox, eggs cracking on your doorknob. The more bizarre and vivid the images, the better they stick. When you need to recall the list, you mentally walk the same route. Each location triggers the image you place there, which triggers the item you wanted to remember. The spatial structure of the route provides organization. The vivid images provide memorability. The technique transforms abstract information, a list of words, into concrete visual spatial information that the brain handles easily. You are not improving your memory. You are using memory for what it is already good at. Memory athletes extend this technique with additional systems. The major system converts numbers into consonant sounds, which become words, which become images. The number 3-2 becomes moon because 3 is represented by M sounds and 2 by N sounds. The number 7-3 becomes calm. Athletes memorize these conversions until they are automatic. Then any number sequence converts instantly into a sequence of images that can be placed in a memory palace. For random words, athletes often use the person action object system. Each word converts to an image of a person doing an action with an object. These triplets are then placed at locations in the memory palace. For faces and names, athletes create exaggerated features of the face and connect them to images representing the name. A person named Baker might be visualized with bread dough for hair. The more absurd the connection, the more memorable. These techniques are not intuitive. They require training. Joshua Foer, a science writer, decided to test whether anyone could become a memory champion with practice. He trained for 1 year under the guidance of Ed Cook, a British memory athlete. Foer practiced daily, building memory palaces, learning the major system, drilling number, and card conversions. In 2006, he won the USA Memory Championship, beating competitors who had been training for years. Foer describes the training as tedious. Progress comes incrementally. Early attempts to memorize a deck of cards take many minutes. With practice, the time drops. The encoding becomes automatic. What initially requires conscious effort becomes fluid and fast. But it always requires effort. Memory athletes do not passively absorb information. They actively transform it using their trained techniques. Remove the techniques, and their memory is normal. Brain imaging studies of memory athletes show no structural differences from control subjects. Their brains are not bigger or differently organized. What differs is activity patterns during memorization. Athletes show increased activity in spatial navigation regions, the hippocampus and parietal cortex, even when memorizing non-spatial information like numbers. They are converting all information into spatial layouts. This is not a different kind of memory. It is standard spatial memory applied to non-spatial content. The implication is crucial. Extraordinary memory is achievable without modifying the brain. You do not need drugs, implants, or genetic engineering. You need training. The limitation is not neural hardware, but learned software. Most people never learn efficient encoding techniques. They try to memorize through repetition, which is slow and ineffective. Memory athletes use elaborative encoding, which is fast and effective because it engages multiple brain systems simultaneously. The techniques work for anyone. Children can learn them. Elderly people can learn them. Brain injury patients with damaged memory systems sometimes cannot learn them, but neurologically normal people of any age can. The barrier is not ability, but motivation. The training is boring. It requires hundreds of hours of practice. Most people are not willing to invest this time for the limited practical benefits. Memorizing card decks is an impressive party trick, but does not obviously improve daily life. Eleanor Maguire at University College London studied London taxi drivers and found their hippocampi were enlarged compared to control subjects. London taxi drivers must pass the knowledge, an exam requiring them to memorize thousands of streets and the fastest routes between locations. Training takes years. The spatial memory demands are extreme. The hippocampus, which supports spatial memory, grows in response to this training. This is neuroplasticity. The brain physically changes based on experience. But the growth is specific. The posterior hippocampus involved in spatial memory enlarges. The anterior hippocampus slightly shrinks. The brain is not gaining capacity, it is reallocating resources. The taxi drivers perform better on spatial memory tasks, but slightly worse on some other memory tasks. Again, we see trade offs. Extreme training in one domain produces both gains in that domain and costs in others. The question becomes whether memory training is worthwhile. For most people, the answer is probably no. Smartphones provide external memory. You do not need to memorize phone numbers or shopping lists when your phone stores them. The practical value of exceptional memory has declined. As information technology has advanced, memory champions compete for sport and personal achievement, not practical advantage. But the principle matters. The brain is trainable. Cognitive abilities that seem fixed can be enhanced through deliberate practice. This is true for memory, but also for attention, reasoning, spatial skills, and other capacities. The enhancement requires effort, and the gains are specific to trained tasks. But it is possible. This is the realistic path to cognitive enhancement, not technological shortcuts, but disciplined training. Memory training also demonstrates what memory is for. Memory athletes do not remember better across all contexts. They excel at arbitrary memorization tasks, cards, digits, words, but they do not necessarily remember conversations better or learn academic material faster. Their trained techniques work for specific kinds of information in specific contexts. Real world memory, remembering what someone told you, integrating new knowledge with existing understanding, involves different processes that do not benefit as much from memory palace techniques. This reveals that memory is not one ability, but many: episodic memory, semantic memory, procedural memory, working memory. These are distinct systems. Training one does not necessarily transfer to others. Memory athletes train specific encoding and retrieval strategies. These strategies help with specific tasks, but do not upgrade the general memory system. You cannot download expertise in memory techniques any more than you can download expertise in piano playing. Both require thousands of hours of practice. The neuroscience is humbling. We want shortcuts. We want pills or devices that make us smarter instantly. But the brain does not work that way. It learns through experience and practice. Shortcuts that bypass experience do not create genuine learning. They create brittle, context specific responses that do not generalize. True learning requires synaptic modification through repeated activation, protein synthesis over hours and days, consolidation during sleep. These processes take time because they involve physical changes in neural tissue. Memory athletes prove that human memory capacity far exceeds what most people achieve. But they also prove that reaching this capacity requires extensive training using specific techniques. There is no easy path. The same brain that forgets appointments can memorize thousands of digits, but only if trained properly. The potential exists in everyone. The actualization requires work. Technology might someday assist this training, making it faster or more efficient. But it cannot eliminate the need for training itself. Memory is skill, and skill requires practice. The practical wisdom is to train memory for tasks that matter. If you need to remember names, Practice face name associations. If you need to remember reading material, practice elaborative encoding. The techniques are known. They work, they just require application. This is less exciting than a memory implantation device, but far more realistic. The enhancement you can achieve through 6 months of dedicated training exceeds what any hypothetical technology might provide decades from now. The tools are available now. The question is whether you are willing to use them. The dream of a pill that enhances memory is old and persistent. Students before exams, professionals facing deadlines, elderly people noticing decline, all would welcome a safe, effective memory drug. The pharmaceutical industry has invested billions searching for such compounds. The results have been largely disappointing. Memory is too complex to be enhanced by simple chemical interventions. But some drugs do affect memory, and understanding how and why clarifies what is possible. Caffeine is the world's most widely used psychoactive substance. Roughly 80% of adults consume it daily. It improves alertness and attention by blocking adenosine receptors in the brain. Adenosine accumulates during waking hours and promotes sleep. Caffeine blocks this signal, making you feel more awake. Better attention indirectly improves memory encoding because you process information more thoroughly. But caffeine does not enhance memory directly. It helps you pay attention, and better attention leads to better memory. The effect is modest. Studies show caffeine improves memory performance in tired or poorly rested subjects, but has minimal effect in well rested ones. This makes sense. Caffeine compensates for sleep deprivation or fatigue. It restores normal function rather than enhancing beyond normal. If you are already alert, more caffeine does not help and may cause anxiety or jitters that impair performance. The dose response curve is inverted U shaped. Some helps too much hurts. Modafinil, marketed as Provigil, is prescribed for narcolepsy and shift work sleep disorder. It promotes wakefulness through mechanisms not fully understood, possibly involving dopamine, norepinephrine, and histamine systems. Studies show modafinil improves attention and working memory in sleep deprived individuals. Like caffeine, it restores normal function degraded by sleep loss. In well rested people, effects are less clear. Some studies show modest benefits, others show no benefit or even impairment on some tasks. The military has studied modafinil for keeping soldiers alert during extended operations. Results suggest it can maintain performance during sleep deprivation better than placebo, though not as well as actual sleep. The drug has side effects: headache, nausea, insomnia, and potential for dependence with chronic use. It is not a cognitive enhancer, but a wakefulness promoter. The memory benefits are secondary consequences of being more alert. Amphetamines and methylphenidate prescribed for attention deficit hyperactivity disorder. Enhance attention and working memory in people with ADHD. In neurotypical people, effects are variable. Some studies show improved focus and better performance on tedious tasks. Other studies show impaired creativity and flexible thinking. The drugs narrow attention, which helps with focused tasks but may hurt with tasks requiring broad attention or creative insight. Students illegally using these drugs for studying often find they study longer but do not necessarily learn more effectively. The mechanism involves increasing dopamine and norepinephrine levels in the prefrontal cortex. This strengthens signals relative to noise, improving concentration. But the brain has optimal neurotransmitter levels. Too little causes inattention. Too much causes rigidity. People with ADHD have suboptimal levels, and stimulants help. People with normal levels may be pushed above optimal, creating different impairments. The inverted U shape appears again. Some is helpful, more is not better. Racetams are a family of compounds promoted as nootropics, cognitive enhancers. Pyracetam is the oldest and most studied. It supposedly improves memory and learning through mechanisms involving neurotransmitter systems and membrane fluidity. However, rigorous clinical trials show minimal effects in healthy adults. Some studies report slight benefits in elderly people with cognitive decline, others report no benefits. The compound is approved in some European countries, but not in the United States, reflecting ongoing uncertainty about efficacy. Countless supplements are marketed for memory: ginkgo biloba, omega 3 fatty acids, vitamin E, B vitamins, phosphatidylserine, huperzine A. Most have minimal evidence supporting their use. Ginkgo biloba has been extensively studied. A large, rigorous trial published in 2008 found it did not prevent cognitive decline in elderly people. Omega 3 fatty acids are important for brain structure, but supplementation above adequate dietary intake does not improve memory in healthy adults. The supplement industry exploits wishful thinking and lacks regulation. Companies can market products with minimal evidence. Consumers assume that if a product is sold, it must work. But supplements face lower regulatory standards than drugs. They do not need to prove efficacy or safety rigorously. Many products contain less of the active ingredient than claimed. Some contain contaminants. The industry profits from hope, despite providing little actual benefit. Why has pharmacological memory enhancement proven so difficult? First, memory involves multiple brain regions and neurotransmitter systems. A drug affecting one system may help one type of memory while impairing another. Second, neurotransmitter systems have optimal levels. Enhancement is not about increasing levels, but about maintaining optimal levels under specific conditions. Third, memory is not one process. Encoding, consolidation, and retrieval involve different mechanisms. A drug improving encoding might not improve consolidation. Fourth, trade offs are ubiquitous. Drugs that improve focus may impair creativity. Drugs that enhance consolidation might reduce sleep quality, which impairs overall cognitive function. Drugs that strengthen memories might reduce the flexibility needed to update or modify memories. The brain is an integrated system. Perturbing one component affects others. Simple interventions produce complex, often undesired consequences. Alzheimer's research illustrates these difficulties. Alzheimer's disease involves progressive memory loss due to neuronal death. Decades of research have identified molecular mechanisms: beta amyloid plaques, tau tangles, inflammation, oxidative stress. Dozens of drugs targeting these mechanisms have entered clinical trials. Almost all have failed. The few drugs approved provide modest, temporary symptom relief without stopping disease progression. The complexity of neurodegeneration has defeated pharmaceutical intervention despite massive investment. The failure of Alzheimer's therapeutics is sobering. If we cannot effectively treat memory loss caused by a specific disease despite knowing many relevant mechanisms, how can we enhance normal memory, which involves even more complex and subtle processes? The optimism of early Alzheimer's research has given way to recognition that neurodegeneration is deeply difficult to reverse. This suggests that enhancing normal memory function may be similarly or more difficult. Memory reconsolidation offers a different pharmacological target. When you recall a memory, it becomes temporarily unstable for several hours before reconsolidating. During this window, the memory can be modified. Propranolol, a beta blocker typically used for high blood pressure, blocks norepinephrine receptors. Studies show that taking propranolol during memory reconsolidation can reduce the emotional intensity of traumatic memories without eliminating the factual memory. This has potential for treating post-traumatic stress disorder. The approach is not memory enhancement, but memory modification. The goal is to weaken problematic memories, not strengthen useful ones. The technique requires precise timing. Propranolol must be taken during the reconsolidation window, shortly after memory retrieval. Multiple sessions may be needed. The effects are specific to the retrieved memory. This is far from a general memory enhancing drug, but may be a useful therapeutic tool. Nootropic enthusiasts often combine multiple substances, creating stacks based on theories about synergistic effects. The problem is that interactions are unpredictable. Each substance affects multiple systems. Combining them multiplies the complexity. Without rigorous testing of specific combinations, users are experimenting on themselves. Some combinations may be harmful. Liver damage, cardiovascular problems, and neurological effects are possible. The lack of regulation means purity and dosing are uncertain. The realistic conclusion is that pharmacological memory enhancement remains largely aspirational. Caffeine helps if you are tired. Drugs for ADHD help if you have ADHD. Treating specific deficits can restore normal function. But enhancing normal memory in healthy people beyond optimizing basic factors like sleep, exercise, and nutrition has not been achieved pharmacologically despite decades of research. The brain's complexity and integrated nature makes simple chemical enhancement unlikely. The dream of a memory pill remains distant. The path forward likely involves personalized medicine, identifying specific deficits in specific individuals and targeting interventions accordingly. One person's memory problems might stem from poor sleep, another's from chronic stress, another's from nutritional deficiencies. Generic memory pills make no more sense than generic pain pills that work for all types of pain. The specificity of memory mechanisms requires specific interventions tailored to specific problems. This is less marketable than a universal memory enhancer, but more scientifically realistic. Elon Musk's Neuralink captured public imagination with videos of a monkey playing video games using only its brain activity. The demonstration was impressive. Electrodes implanted in the monkey's motor cortex recorded neural signals as the monkey moved a joystick. A computer decoded these signals and learned to predict intended movements. Then the joystick was disconnected. The monkey continued thinking about moving the joystick, and the computer translated those thoughts into cursor movements. The monkey learned to play Pong mentally, earning banana smoothie rewards for successful plays. This is genuine brain computer interface technology. It works, but it is also far simpler than it appears. The motor cortex has been mapped extensively. Specific neurons fire when planning specific movements. Recording from hundreds of neurons provides enough information to decode intended movements with reasonable accuracy. This is input from brain to computer, reading intentions. The hard problem is output from computer to brain, creating sensations or memories. The Utah array, developed in the 1990s, remains the gold standard for invasive brain recording. It consists of a small grid of 96 needle electrodes, each penetrating a few millimeters into cortical tissue. The array records electrical activity from neurons near each electrode. Signal processing algorithms decode patterns in this activity, inferring intended movements, speech, or other cognitive states. Paralyzed patients have used Utah arrays to control robotic arms, type on virtual keyboards, and even regain some movement of their own limbs through functional electrical stimulation. Leigh Hochberg leads the BrainGate Consortium studying brain-computer interfaces for paralysis. Participants with Utah arrays implanted in motor cortex can control computer cursors, robotic arms, and other devices through thought. One participant, a woman paralyzed by a stroke, used the system to drink coffee from a bottle held by a robotic arm she controlled mentally. The achievement is remarkable, representing years of neuroscience, engineering, and clinical work. But it is also limited. The control is slow and requires intense concentration. The system requires calibration before each use, and it reads only motor intentions, not complex thoughts or memories. Neuralink's advance over Utah arrays is primarily miniaturization and channel count. Their device has 1,204 electrodes, about 10 times more than a Utah array. The electrodes are thinner, potentially causing less tissue damage. The device is wireless, eliminating infection risks from transcutaneous connectors. These are genuine engineering improvements, but the fundamental capability remains the same, recording electrical activity from hundreds or thousands of neurons out of billions and decoding patterns in that activity. The output problem is far harder. How do you write information into the brain? Electrical stimulation can activate neurons, but crude stimulation does not create meaningful sensations or memories. Visual cortex stimulation creates phosphenes, spots of light, not recognizable images. Auditory cortex stimulation creates buzzing or clicking sounds, not speech. Somatosensory cortex stimulation creates tingling or pressure sensations, not the rich tactile experience of touching an object. Cochlear implants represent the most successful brain-computer interface output. These devices convert sound into electrical signals delivered to the auditory nerve. About 1 million people worldwide have cochlear implants. Users can understand speech and hear environmental sounds, but the sound quality is poor compared to natural hearing. Music sounds mechanical. Subtle acoustic details are lost. The device works because the auditory system is relatively simple. Sound has one dimension, frequency, and the cochlea is organized tonotopically with different frequencies activating different locations. Even so, it took decades to develop effective stimulation strategies. Visual cortex prosthetics aim to restore vision to blind people. Electrodes implanted in visual cortex can create phosphines by stimulating neurons. Multiple phosphines can form simple images, letters, shapes, edges, but creating rich visual experience requires stimulating millions of neurons in precise patterns. Current devices have at most a few thousand electrodes. The resulting vision is crude, low resolution, black and white, no depth perception. It is useful for basic navigation, but nowhere near natural vision. The complexity gap is vast. Cochlear implants work because they bypass the auditory nerve and deliver signals to a well understood structure with clear frequency mapping. Visual prosthetics try to bypass not just the optic nerve, but the entire retina and its complex preprocessing. The visual cortex expects preprocessed signals, not raw light information. Delivering raw information overwhelms the system or produces meaningless noise. Even if you could stimulate every neuron in visual cortex, you would not know which patterns create which perceptions. The neural code is not understood. Memory is orders of magnitude more complex than vision. A memory involves distributed activity across multiple brain regions: visual cortex, auditory cortex, motor cortex, hippocampus, amygdala, prefrontal cortex. These regions must activate in coordinated patterns with millisecond timing. The patterns are unique to each person and each memory. There is no simple mapping like the tonotopic organization of audition or the retinotopic organization of vision. Stimulating neurons randomly does not create memories. It creates confusion or seizures. The writing problem also involves synaptic plasticity. Natural memory formation changes synaptic strengths through protein synthesis over hours. Artificial stimulation can make neurons fire, but does not necessarily trigger the molecular cascades that strengthen synapses. Brief stimulation produces brief activity without lasting change. To create a lasting memory, you need sustained pattern stimulation that mimics natural learning. This requires knowing which neurons to stimulate, in what patterns, for how long. We do not have this knowledge for any complex memory. Non invasive brain stimulation techniques avoid surgery, but have less precision. Transcranial magnetic stimulation uses magnetic fields to induce electrical currents in brain tissue. It can activate or inhibit regions temporarily. Clinical uses include treating depression by stimulating prefrontal cortex, but the spatial resolution is poor, several centimeters. You cannot target individual neurons or even small groups. The effects are general region level changes in excitability, not precise control of neural activity. Transcranial direct current stimulation passes weak electrical currents through the skull, slightly increasing or decreasing neural excitability in large brain regions. Some studies report improved learning when applied during training. Other studies report no benefits. Meta analyses suggest effects are small and inconsistent. The mechanism is unclear. The stimulation may help some people in some contexts, but is far from reliable cognitive enhancement. It certainly does not implant memories. Ernal, founded by Brian Johnson, develops non-invasive brain imaging devices. Their technology measures neural activity through the skull using advanced sensors. This is useful for research and potentially for diagnostics. But measuring is easier than manipulating. The devices provide better input from brain to computer. They do not provide output from computer to brain. Reading neural activity, even with high resolution, does not enable writing memories. The timeline problem is sobering. Cochlear implants were first demonstrated in the 1960s. It took decades to develop them into reliable, useful devices. We are now in the early stages of visual prosthetics and motor brain computer interfaces. These address sensory and motor functions, the simplest brain systems, higher cognition, memory, reasoning, language comprehension, involves vastly more complex neural processes. If sensory prosthetics take decades to develop, cognitive prosthetics may take centuries if they are possible at all. The hype around brain computer interfaces often conflates different capabilities. Reading motor intentions to control a cursor is impressive engineering, but says nothing about reading or writing complex thoughts. Demonstrating that a paralyzed person can type with brain control is a meaningful achievement for accessibility. It does not suggest that downloading memories is near. The capabilities are different by orders of magnitude in complexity. Realistic near term applications focus on restoring lost function. Brain computer interfaces might help paralyzed people control computers or prosthetic limbs. Deep brain stimulation helps Parkinson's patients control tremors. Targeted electrical stimulation might treat epilepsy or depression. These are valuable goals addressing serious medical needs. They are also far more limited than science fiction brain computer interfaces that upload skills or transfer consciousness. The ethical landscape differs drastically between therapeutic and enhancement applications. Helping paralyzed people regain communication justifies significant risks. The benefit is enormous, and alternatives are few. Enhancing normal cognition in healthy people justifies minimal risk. The benefit is unclear, and alternatives exist: education, training, lifestyle changes. Regulatory agencies will demand much higher safety standards for enhancement than for therapy. This creates a high bar that may never be cleared. The fundamental lesson is that input and output are asymmetric. Reading brain activity is difficult but achievable with current technology. Writing information into the brain in a form that creates meaningful experiences or memories is far harder and may be impossible with any foreseeable technology. The brain's own mechanisms for creating memories, experience, attention, rehearsal, sleep, work because they engage the entire system properly. Artificial shortcuts that bypass natural processes either fail to create lasting changes or create changes that disrupt normal function. Brain computer interfaces will advance. Recording resolution will improve. Decoding algorithms will become more sophisticated. Wireless implants will become safer and more durable. These advances will enable better assistive devices for people with disabilities. They will enable new research into brain function, but they will not enable memory implantation in the science fiction sense. The gap between reading neural activity and writing specific memories into a functioning brain is not an engineering gap, but a conceptual one. Memory is not information to be transmitted, but structure to be grown through natural processes that cannot be circumvented without destroying what makes memory meaningful. Suppose the technology existed. Suppose you could safely implant complex memories, skills, and knowledge directly into someone's brain. The philosophical and ethical problems would only begin. Who decides what memories to implant? Who has access? What happens to human development, education, and identity? These questions have no clear answers, yet they must be confronted before the technology exists if we hope to regulate it wisely. Educational inequality would be amplified exponentially. Currently, wealthy children attend better schools, receive tutoring, and have resources that poor children lack. This creates advantage, but not unbridgeable gaps. A poor child with determination can still learn what wealthy children learn through public libraries, free online resources, and scholarships. The playing field is uneven, but not closed. Memory implantation would change this fundamentally. If wealthy parents could buy their children instant fluency in 5 languages, advanced mathematics, and expert knowledge in multiple fields, the gap becomes unbridgeable. Poor children could never catch up through hard work because the wealthy children would have decades of learning implanted in hours. The meritocracy mythology would collapse. We tell ourselves that success comes from talent and effort. This is partly false already. Luck and privilege matter enormously, but the mythology serves a function. It motivates effort and provides a basis for considering outcomes somewhat fair. If memory implantation were available only to the wealthy, success would be purely a function of wealth. Those born poor would face cognitive aristocrats who had literally purchased superior minds. This might trigger class resentment exceeding anything history has seen. Some argue that eventually costs would fall and technology would democratize, like smartphones and internet access. But memory implantation requires invasive brain procedures. Unlike smartphones, you cannot mass produce brain surgery. Each procedure requires skilled surgeons, sterile facilities, and individualized planning. The scaling economics differ fundamentally. Even if costs fell substantially, they would remain high enough to create prolonged inequality. During this period, which might last generations, society would stratify into enhanced and natural humans, with consequences that would echo for centuries. Access restrictions would be fiercely debated. Should memory implantation be allowed at all? If allowed, should it be restricted to therapeutic uses, restoring memory lost to injury or disease? Should enhancement be permitted for competitive advantage in education or employment? Should parents be allowed to enhance their children? Each question opens chasms of disagreement. Libertarians would argue that individuals have the right to modify their own bodies and minds however they choose. If an adult wants memory enhancement and can afford it, no one should prevent them. Restricting access is paternalistic interference with personal autonomy. Conservatives might argue that human nature should not be technologically modified, that enhancement violates the sanctity of natural human development. Progressives might argue that access should be universal or prohibited entirely to prevent exacerbating inequality. No position is obviously correct. Each reflects deep values about autonomy, equality, and human nature. Children present special problems. Parents make medical decisions for children. Should they be allowed to make enhancement decisions? A parent who believes memory enhancement will benefit their child will want to provide it. A parent who believes it will harm development or identity will refuse it. But children cannot consent. They cannot judge whether they want their memories and identity modified. Making permanent changes to a child's brain based on parental preference seems wrong, yet we allow parents to make many significant decisions affecting children's development. Where is the line? Coercion risks are severe. Employers might require memory implantation as a condition of employment. If a company can hire an employee with implanted expertise, why would they hire someone who must learn naturally? This creates pressure to enhance. Refusal means unemployment. The choice becomes coerced, technically voluntary but practically necessary. Similar dynamics would affect education. Schools might require students to have certain implanted knowledge as prerequisites. Military services might require soldiers to have implanted combat skills. What begins as optional becomes mandatory through institutional pressure. Identity theft acquires a terrifying new meaning. If memories can be implanted, they can presumably be extracted. Your memories contain your entire life history, including passwords, personal relationships, embarrassing moments, and private thoughts. A technology that writes memories might also read them. This is the ultimate privacy violation. Someone could know everything you have ever thought or experienced. The implications for blackmail, manipulation, and control are dystopian. Corporations would seek to exploit memory technology. Advertising could implant positive memories of products. Political campaigns could implant false memories of opponent misdeeds. Employers could implant loyalty or compliance. Religious organizations could implant fervent belief. Every institution that currently influences people through persuasion would seek to do so directly through memory manipulation. The line between persuasion and coercion would dissolve. If I implant the memory that I saved your life, you will feel gratitude and loyalty to me, even though the event never occurred. This is mind control. Criminal justice becomes incoherent. If memories can be implanted, eyewitness testimony becomes completely unreliable. Currently, Elizabeth Loftus's research on false memories creates reasonable doubt. With memory implantation, any memory could be artificial. Defendants could claim their confession memories were implanted. Victims could have false memories of crimes that never occurred. The entire evidentiary system based partly on memory would collapse. New forensic methods would need to distinguish real from implanted memories, if such distinction is even possible. Alternatively, criminal justice might use memory implantation as punishment or rehabilitation. Instead of imprisoning criminals, implant memories of experiencing their victims' suffering. Implant aversion memories for crimes they are tempted to commit. Erase memories of criminal skills. This raises obvious ethical concerns. Forcibly altering someone's mind as punishment seems to violate human dignity more profoundly than imprisonment. Yet some might argue it is more humane than years in prison and more effective at preventing recidivism. Military applications are inevitable if the technology exists. Create soldiers without fear by suppressing amygdala memories. Implant combat skills so training takes days instead of months. Erase traumatic memories to prevent post-traumatic stress disorder. These applications would appeal to military planners. They would also create soldiers who are less human, modified for combat effectiveness without regard for psychological wholeness. History's treatment of veterans suggests society would adopt such technology if available and deal with consequences later. Existential risks emerge at scale. If large populations have modified memories, collective memory becomes unreliable. Society's understanding of its own history depends on individuals remembering and transmitting their experiences. If those memories can be manufactured, historical truth becomes contested in new ways. Authoritarian governments could implant false memories of past events to justify present policies. Democratic governments could face populations with incompatible memory sets, making consensus impossible. The regulation challenge is immense. Imagine trying to write laws governing memory implantation when the technology does not yet exist and its capabilities are uncertain. Regulate too strictly, and you prevent beneficial applications and drive development underground or offshore. Regulate too loosely, and exploitation and harm proliferate. International coordination would be necessary but difficult. If one country bans memory enhancement while another allows it, enhanced individuals from the permissive country have advantages that create competitive pressure for other countries to allow it. The conversation about these issues must happen now, before the technology exists. Once it exists, economic and strategic incentives will drive deployment faster than ethical reflection can occur. This is the pattern with most technologies: development first, regulation later, after harms have occurred. Nuclear weapons, social media, facial recognition, gene editing all follow this pattern. Memory implantation is potentially more consequential than any of these because it strikes at the core of personhood. Some argue that concerns are premature. The technology may never exist. Why worry about problems that may never arise? This argument ignores that the path to technology is long, with many decision points. Choices made now about research priorities, funding, and ethical frameworks shape what becomes possible later. If researchers and funders believe memory enhancement is a worthy goal, resources flow toward it. If society decides the risks outweigh benefits, resources flow elsewhere. The conversation shapes the future. Others argue that technology is inevitable. If memory implantation is possible, someone will develop it. Ethical objections will not stop determined researchers. This argument counsels acceptance and attempts to maximize benefits while minimizing harms. But accepting inevitability does not require embracing enthusiasm. Society can decide that some technologies, even if possible, should not be developed. We have mostly refrained from human cloning despite technical capability. We could refrain from memory implantation, even if it becomes possible. The deepest question is whether we should want this technology to exist. Setting aside whether it will exist, should we hope for it? The answer depends on what we value about human life. If we value authentic experience, earned achievement, and the meaning that comes from struggle, then memory implantation threatens core values. If we value outcomes over processes, reduction of suffering, and expansion of human capabilities, then memory implantation might seem desirable. There is no resolving this conflict through logic alone. It reflects fundamental value differences. The ethical minefield awaits us whether or not we choose to enter it. If the technology remains impossible, the questions are academic but still useful for understanding what we value. If the technology becomes possible, the questions become urgent and the stakes become the future of human nature itself. The time to think through these issues is now. While they remain hypothetical, and discussion can be calm and thorough. Once the technology exists, pressure and panic will dominate. The quality of our thinking now will determine the quality of our choices then. We have explored memory from molecules to morality, from neurotransmitters to neural networks, from what we know to what we fear. Now return to this moment. You are lying in darkness, listening to these words, drifting towards sleep. Your brain is preparing for its nightly work. This work is more sophisticated than any technology discussed in this exploration. Your brain will consolidate today's memories naturally, without devices or drugs, through processes refined by hundreds of millions of years of evolution. Sleep is when memory becomes permanent. During slow wave sleep, your hippocampus replays today's experiences. Neural patterns that fired during waking replay during sleep, but faster and in coordinated bursts. Each replay strengthens the synapses involved. The memory transfers gradually from hippocampus to cortex. This process cannot be rushed. It requires hours of uninterrupted sleep, cycling through stages, each stage serving specific functions in memory consolidation. Rapid eye movement sleep serves a different function. During REM sleep, the brain synthesizes and integrates information. Memories connect to existing knowledge. Patterns emerge from disparate experiences. Emotional memories are processed, their intensity modulated. Dreams may serve to explore variations on recent experiences, testing possible interpretations and responses. This creative integration cannot occur without REM sleep. When deprived of REM, people show impaired emotional regulation and reduced creative problem solving. The modern world assaults sleep. Artificial light delays circadian rhythms. Screens emit blue light that suppresses melatonin. Caffeine consumed too late persists in the bloodstream. Stress hormones remain elevated into night. Work demands encroach on sleep time. The result is an epidemic of sleep deprivation. Adults in industrialized nations sleep 1 to 2 hours less per night than humans did a century ago. This chronic deprivation carries profound costs. Memory suffers first and most obviously from poor sleep. After one night of poor sleep, encoding of new memories drops by 40%. The hippocampus cannot effectively form new memories when sleep deprived. After several nights, consolidation also suffers. Memories formed during the day fail to transfer to long-term storage. You retain less of what you learned. Students who stay up all night studying perform worse than those who study moderately and sleep well. The all-nighter is counterproductive because sleep is when learning solidifies. Chronic sleep deprivation causes measurable brain changes. The hippocampus shrinks. White matter integrity decreases. Amyloid plaques accumulate more rapidly, potentially increasing Alzheimer's risk. These effects are not merely correlation. Sleep deprivation experiments in animals show that insufficient sleep directly causes brain damage. The glymphatic system, which clears waste products from the brain, operates primarily during sleep. Without adequate sleep, toxic proteins accumulate. The relationship between sleep and memory is bidirectional. Poor sleep impairs memory formation. Memory problems cause sleep disturbance. People with insomnia often ruminate, replaying worries and regrets. This rumination prevents sleep onset. The resulting poor sleep further impairs emotional regulation and memory consolidation, creating a vicious cycle. Breaking this cycle requires improving sleep, which then improves memory naturally. The irony is profound. We fantasize about technological memory enhancement while damaging our natural memory systems through sleep neglect. We want drugs to make us smarter while consuming drugs that make us dumber. We search for neural implants while ignoring the neural maintenance our brains desperately need. The solution to memory problems is often not advanced technology, but basic sleep hygiene. Sleep hygiene sounds boring because it is boring. Keep consistent sleep and wake times. Darken your bedroom. Cool the room to 65 to 68 degrees Fahrenheit. Limit caffeine to morning hours. Exercise regularly, but not near bedtime. These recommendations lack the excitement of memory implants or smart drugs, but they work. They work better than any current pharmaceutical or technological intervention for memory enhancement. The modern cult of productivity treats sleep as weakness. Sleeping only 4 hours and boasting about it becomes a status symbol in some corporate cultures. This is catastrophic for cognitive function. Every hour of sleep debt impairs you measurably. Studies comparing people after full sleep, moderate sleep restriction, and severe sleep restriction find that even moderate restriction, 6 hours instead of 8, accumulates impairment comparable to complete sleep deprivation. And sleep deprived people often do not recognize their impairment. They feel fine while performing poorly. The fantasy of technological shortcuts appeals because behavioral change is difficult. Sleeping more requires saying no to evening commitments, turning off entertainment, lying in darkness for 8 hours. This is less appealing than imagining a pill or device that eliminates the need for sleep or makes 5 hours function like 8, but such technologies do not exist despite enormous military interest in finding them. Modafinil keeps you awake, but does not replace sleep's restorative functions. Deprivation accumulates even while you feel alert. Children and adolescents are particularly vulnerable. School start times misalign with adolescent circadian rhythms, forcing teenagers to wake before their brains are ready. Homework loads encroach on sleep time. Electronic devices provide stimulation late into the night. The result is that most teenagers are chronically sleep deprived during crucial periods of brain development. Their academic performance suffers. Their emotional regulation suffers. Their memory formation suffers. Changing school start times later improves outcomes, but many districts resist due to logistical challenges. Elderly people often experience sleep fragmentation. They wake frequently and spend less time in deep, slow wave sleep. This contributes to the memory decline associated with aging. While some sleep changes with age are natural, many are preventable. Treating sleep apnea, reducing medications that impair sleep, maintaining consistent schedules, and ensuring adequate light exposure during the day all improve sleep quality in older adults. Memory often improves as a result. The relationship between sleep and dreams fascinates, but remains mysterious. Dreams occur primarily during REM sleep, though also during other stages. They involve vivid sensory experiences, narrative elements, emotional intensity, and often bizarre logic. Whether dreams serve functions or are merely byproducts of neural activity is debated. Some evidence suggests dreams help process emotional memories, reducing their distress while retaining factual content. Other evidence suggests dreams explore counterfactuals, testing possible interpretations of ambiguous situations. Memory for dreams is notoriously poor. Most dreams are forgotten within minutes of waking. Dreams remembered vividly fade rapidly unless rehearsed immediately upon waking. This forgetting may be adaptive. Dreams contain random associations and impossible scenarios. Treating them as real memories would create confusion. The brain may actively suppress dream memories to maintain distinction between imagination and reality. Only salient or emotionally intense dreams are retained. Lucid dreaming occurs when you become aware you are dreaming while still asleep. Some people lucid dream naturally. Others train the ability. Lucid dreamers can sometimes control dream content, exploring virtual realities constrained only by imagination. This is as close as we currently come to the science fiction scenario of immersive virtual experiences. But even lucid dreams are not memory implantation. They do not create skills or lasting memories. They are experiences occurring entirely within your existing neural patterns. The practical wisdom is simple but essential. Prioritize sleep. Treat it as non negotiable as eating or breathing. Your memory depends on it. Your cognition depends on it. Your emotional well being depends on it. No technology on the horizon can replace what sleep does naturally. The 8 hours you spend sleeping each night are not wasted time. They are when your brain processes the 16 hours you spent awake, extracting meaning, consolidating learning, preparing for tomorrow. This exploration of memory implantation technology has revealed a paradox. We seek technological enhancement while neglecting biological maintenance. We dream of downloading knowledge while sleep deprived brains struggle to consolidate normal learning. We want to augment cognition with devices while damaging cognition with lifestyle. The solution is not abandoning technological dreams, but recognizing that biology sets constraints technology cannot circumvent. Memory is not data to be transferred, but structure to be grown through experience. Learning is not information transfer, but synaptic modification through use. Enhancement comes not from shortcuts, but from optimizing natural processes sleep, attention, encoding strategies, rehearsal, retrieval practice. These are unsexy truths. They promise no quick fixes, but they work because they align with how brains actually function. The 8 hours you spend sleeping represent your nightly investment in memory consolidation. During these hours, your brain performs miracles no technology can match. Synapses strengthen and weaken according to use. Proteins synthesize and restructure neural connections. Waste products clear from tissue. Memories integrate with existing knowledge. All of this happens automatically, requiring only that you lie still in darkness and allow it to proceed. This is the technology you already possess. Use it well. Your memories depend on it. Your identity depends on it. Your future self depends on the maintenance you provide tonight. Memory's imperfection is not a flaw awaiting correction. It is a design feature that makes human cognition adaptive, creative, and meaningful. Evolution did not optimize memory for accuracy. It optimized memory for survival, which requires forgetting, distortion, and reconstruction. A brain that remembered everything would be a brain that could do nothing. The flexibility that makes memory unreliable also makes it powerful. Forgetting enables learning. When you learn a new concept, you initially remember surface details the color of the textbook, the room where you studied, the specific examples used. Over time, these details fade. What remains is the abstract principle. This is not memory failure. This is successful abstraction. Your brain has extracted the generalizable pattern and discarded irrelevant specifics. You learn the concept of triangle by seeing many triangles and forgetting their particular colors, sizes, and contexts. The forgetting is the learning. Solomon Shereshevsky, with his virtually unlimited memory, struggled with abstract thinking because he could not forget the concrete details. Each word triggered such rich associations that extracting abstract meaning became difficult. His memory was too good to be useful. This is not hypothetical. It is documented case history. Perfect memory impairs cognition by preventing the abstraction that makes knowledge applicable beyond specific instances. Memory's malleability allows growth and healing. When you remember a painful event, you do not replay an unchangeable recording. You reconstruct the memory from distributed fragments. Each reconstruction offers opportunity for reinterpretation. The event that devastated you at 20 may become, at 30, a source of strength because you have reinterpreted it. The memory changed because you changed. Static memory would trap you in past emotional states. Malleable memory allows psychological evolution. Post traumatic stress disorder demonstrates what happens when memory becomes too rigid. Traumatic memories intrude involuntarily, replaying with full emotional intensity. The sufferer cannot update or recontextualize them. Treatment works by helping the person recall traumatic memories in safe contexts, allowing reconsolidation with reduced emotional intensity. The treatment exploits memory's malleability. If memory were perfectly stable and accurate, trauma would be incurable. The very property that makes memory unreliable, reconsolidation, is what makes healing possible. The self is not data storage, it is an ongoing process of becoming. Your identity today is constructed from memories of who you were yesterday and projections of who you want to be tomorrow. These memories are not accurate historical records. They are narratives revised constantly to maintain coherence as you change. The person you are at 40 cannot fully understand the person you were at 20 because you have reinterpreted all those memories. You have become someone new while maintaining continuity through narrative revision. If memory were perfect and unchangeable, personal growth would be impossible. You would be trapped as whoever you were when key memories formed. But memory is plastic. As you grow and change, your memories change to remain consistent with your current self. This allows identity to be both continuous and evolving. The same mechanism that makes eyewitness testimony unreliable makes personal transformation possible. You cannot have one without the other. When you work for hours to understand a concept, the effort creates rich neural connections between that concept and existing knowledge. The struggle itself encodes the memory. Easy learning creates weak memories. Difficult learning creates strong memories because difficulty requires engagement, attention, and integration with prior knowledge. If you could download understanding instantly, you would have weak memories lacking connection to the rest of what you know. The knowledge would be isolated and fragile. Expertise develops through 10,000 hours of deliberate practice, not because 10,000 hours is an arbitrary threshold, but because expertise requires building vast networks of connections between pieces of knowledge. Each connection must be forged through experience. Shortcuts that bypass this process create the appearance of expertise without the underlying structure. The person who has downloaded martial arts techniques but never practiced them will be defeated by someone with less knowledge but more training, because training builds not just knowledge, but the integrated neural patterns that enable automatic, skilled performance. Meaning emerges from causal connection between experience and memory. Your grandmother's kitchen matters because you were there with your grandmother. The memory has value because it is connected causally to experiences that shaped you. If someone implanted identical memories, the same visual details, the same emotions, those memories would lack meaning because they are not connected to your life history. They would be simulacra without substance. The causal history matters as much as the content. This is why authenticity matters. People value real experiences over simulated ones, even when the simulations are subjectively indistinguishable. Robert Nozick's experience machine thought experiment reveals this. Given the choice to plug into a perfect simulation of a wonderful life or to live a real but more difficult life, most people choose reality. They value actually doing things, not just experiencing doing them. Memory implantation would be a partial experience machine, giving you memories without the experiences. For most people, this would feel hollow. Human connection depends on shared struggle. When you learn something difficult alongside others, the shared experience creates bonds. You understand each other's challenges because you face them together. If some people had knowledge implanted while others learned naturally, they would lack this shared ground. The implanted knowledge would be a barrier to connection because it was not earned through experience. Community requires common experience, and shortcuts that bypass experience undermine community. Wisdom cannot be implanted because wisdom is not information. It is judgment developed through experience, failure, and reflection. A young person with downloaded knowledge of every philosophical text would not be wise. They would lack the life experience to apply that knowledge appropriately. Wisdom requires not just knowing what is true, but knowing when and how to apply it. This comes only from making mistakes, suffering consequences, and learning from them. There is no shortcut. The fantasy of instant learning reveals fear of inadequacy and desire for transformation without growth. These are understandable human yearnings. We all feel inadequate sometimes. We all wish we could change without the painful process of changing. But acting on these yearnings would eliminate what makes achievement meaningful. Accomplishment matters because it was difficult. If it were easy, it would be worthless. A world where everyone could download expertise would be a world where expertise had no value. The limitations of memory are the limitations that make us human. We forget, so we learn to record important information externally. We distort, so we learn to corroborate and question. We struggle, so we value achievement. We change, so we are not trapped by our past. These limitations are not problems to be solved. They are features that make human life meaningful. Technology that eliminated them would not enhance humanity, it would diminish it. Perhaps some technologies should remain science fiction. Perhaps the gap between what we can imagine and what we should pursue is wisdom rather than limitation. Memory implantation technology, if it ever becomes possible, would force choices about human nature that we may not be ready to make. It would offer capabilities we should refuse. The power to rewrite minds is a power that corrupts because it is too fundamental to identity and autonomy to be wielded safely. The alternative to technological shortcuts is embracing natural processes. Sleep consolidates memories. Practice builds skills. Reflection creates wisdom. Community provides support. These are old truths, unfashionable in an age that values innovation and disruption. But they are true. They work because they align with how humans actually function. Enhancing human life comes not from circumventing our nature, but from fully engaging it. Tonight, as sleep approaches, your brain will perform its ancient work. Memories will consolidate, emotions will process, neural connections will strengthen and prune. This happens whether you understand it or not. It happens because hundreds of millions of years of evolution have optimized it. No human invention matches this sophistication. The technology you seek is the technology you already possess. It requires only that you use it. Sleep well, attend carefully, practice diligently, reflect honestly. The quantum fantasy, the nanobot dream, the memory implant vision, these are projections of our discontent with limitation. But limitation is not the enemy, it is the structure that makes meaning possible. A being with perfect memory and infinite knowledge would be incapable of surprise, growth, or joy. The forgetting that frustrates you enables the learning you value. The struggle that exhausts you creates the achievement that satisfies you. The imperfection that worries you is the space where wisdom grows. Let the fantasy recede. Let the science fiction remain fiction. What you have is enough. Your brain, imperfect and struggling, is the most complex structure in the known universe. It contains 86 billion neurons, 600 trillion synapses, countless possibilities. It creates your memories, your identity, your world, not by downloading data, but by living experience. Not by perfect recall, but by meaningful reconstruction. Not by technological enhancement, but by natural growth. Sleep now, dream freely. When morning comes, you will remember some dreams and forget others. You will recall yesterday's experiences with some accuracy and some distortion. You will be slightly different from who you were today because your memories will have reconsolidated differently. This is not failure. This is how memory works. This is how you work. This is enough. This has always been enough. The technology you need is the tissue you have. Use it well. Protect it through sleep. Honor it through attention. Grow it through experience. That is the path to better memory. That is the path to a meaningful life. No shortcuts, no downloads, just the slow, imperfect, beautiful process of becoming yourself through each remembered day and each consolidating night.